Big warm welcome to everyone to this exciting event where we celebrate the National Space Day and the incredible achievement of Chandrayaan 3 landing on the moon. Today's event is a special one, jointly organized by IIT and SAC ISRO. Space Application Center, located in Ahmedabad, is a major research and development center of the Indian Space Research Organization. It plays a key role in realizing vision and mission of ISRO. Today, we have gathered here to celebrate the past, present, and future of space exploration.
Just last year, on August 23, 2023, India achieved a historic milestone by successfully landing its Chandrayaan 3 Vikram lander on the lunar South Polar region. In recognition of this remarkable feat, the Government of India has declared August 23rd as National Space Day. With this achievement, India became the fourth country to land on the moon and the first to reach the southern polar region. Today, we have an amazing lineup of speakers who will take us on a journey through space science, technology, and the possibilities that lie ahead. So whether you are a curious school student or an aspiring MSc or BTech student, there is something here for everyone.
To commence our program on an auspicious note, we will now light the ceremonial lamp. I would like to invite the Director of SAC ISRO, Shri Desai, all our esteemed guests for the day, and Professor Anand to join us in this tradition. Thank you so much, everyone. Now let's take a moment to welcome our distinguished guests, speakers, and of course, all of you, the future of space exploration. I would like to invite Professor Anand to present a bouquet and a token of respect to the Director of SAC ISRO, Shri Nilesh Desai, distinguished scientist and Director of SAC. Ahmedabad, a lead center of ISRO for design and development of space-borne instruments and associated applications. I would also request Professor Anand to present a bouquet and a token of respect to our esteemed speakers for the day. Our first speaker for the day is Shri Pradeep Soni, scientist, SAC ISRO. Shri Soni played an important role in Chandrayaan 3 as project manager for the design and development of lander imagers and rover imager. Next we have is Professor Gulab Dewangan. Professor Dewangan is a well-known astrophysicist at the Inter-University Center for Astronomy and Astrophysics, Pune. He has led several successful observing proposals in NASA and ISRO missions. Next we have is Professor Shashi Ganesh. Dr. Ganesh is a professor in the Astronomy Division of Physical Research Laboratory. He has interest in observational astronomy and the development of instruments for telescopes operated by PRL at the Mount Abu Observatory.
Next we have Professor Suresh from IUCAA, Pune. Professor Davari is a physicist and works at IUCAA with a team of engineers and scientists responsible for building LIGO India. Next we have Shri Pranav Singh, the Deputy Director of Program Management and Authorization at InSpace. InSpace is an autonomous single-window agency to regulate, authorize, enable, promote, and supervise all space activities undertaken in the country.
Thank you very much, sir, for doing the honor. So, to kick off our program, I'm delighted to invite the Director of SAC ISRO, Shri Nilesh Desai, to deliver a brief welcome address.
Good morning, all. Suprabhatam, dignitaries on the dais, our distinguished scientists and guests from various institutes, PRL as well as IUCA. Welcome to all of you, sir. Nice meeting you. And my dear colleagues, Mr. Pradeep, Soni, and PP Singh from ISRO Ahmedabad, and all the dear participants and the organizers from IIT Gandhinagar. So, at the outset, let me thank the organizers at IIT Gandhinagar and my team here from Space Application Center for organizing this event, and especially special thanks to our distinguished speakers for this program. And let me first apologize. I generally start my all addresses with either disclaimers or apologies. So today it is turn of apology for being slightly late for this program. So George Bernard Shaw used to say that generally we feel better late than never. ना जाओ उससे तो better है कि पहुंच जाओ थोड़ा late तो late. But he used to say that better never than late. क्योंकि लेट हो गए तो आपकी जाओ ही नहीं फिर कि बना दो कि कुछ काम आ गया था इसलिए so that आपकी जो इज्जत है वो बनी रहे कि नहीं तो लोग बोलेंगे कि ये लेट ही आते हैं हमेशा. Anyway, sorry for this late start of this program. So as all of you know, National Space Day, Government of India has pronounced 23rd August as the celebration for National Space Day. We have been celebrating National Science Day, 20th February, National Technology Day, 11th May. So in that, this one more celebration has been added. Generally, you say that in your boring life, we should have celebrations. So already in India, we have many religions, so we celebrate our religions, our other occasions, our birthdays, and many other occasions. We are in search of such occasions. But this has been really a very nice occasion to really celebrate. So as somebody pointed out, that India has been the fourth country and the first to land on the South Pole. So in that sense also, it is a really occasion to celebrate. And especially, जैसे बच्चे का फर्स्ट बर्थडे हम बहुत अच्छी तरह मनाते हैं ना, तो दिस इज लाइक आवर फर्स्ट बर्थडे ऑफ सेलिब्रेटिंग लैंडिंग ऑन मून. सो इन दैट सेंस ऑल्सो दिस ईयर गवर्नमेंट हैज डिक्लेयर्ड, सो कैबिनेट सेक्रेटरी कॉल्ड ऑल दी secretaries of the various government department that we should celebrate this event in a big way. So last few days and up to 23rd August, all over India we are celebrating these events in different forms. So this occasion is culmination of that effort. So here in and around Ahmedabad, we have celebrated this event at different places, schools, colleges, research institutes, and in that line, IIT Gandhinagar is organizing this event today, and I'm glad that so much presence is there from various different schools nearby. So at the outset, let me thank all of you for participating in this event, and I'm sure that you will benefit by the erudite presence of all my distinguished colleagues here, not only from SAC ISRO, but from PRL and other IUCA and other our very expert scientists from all over the country. So I'm sure that you will definitely enjoy this occasion, and it is also not only for enjoyment, it is for learning also. So in that sense also, it will be very useful to especially the students who aspire to be our future scientists. So we are in lookout for good scientists. So I'm sure that many of you will make it to ISRO or PRL or IUCA or many other places after going through your natural grill of studying through your graduation and many other educational laurels. So let me once again thank all of you, and I'm sure that you will benefit by this experience. Now, coming to space. Space is a very hazardous place. All of you know that, unlike Earth. So, why hazardous? Because there are extreme temperatures, cold and hot. There is a vacuum. So, vacuum adds to that extremity. And then there is radiation. So, all this put together will make it very hostile. So, to survive in space, it's really difficult. And that's why everywhere we are always looking for life somewhere else. Because many of these endeavors, especially this interplanetary research and many other astronomical observations which we do either from Earth or from space, is mainly directed towards finding out whether any life is there somewhere else or not. I am a non-believer because I am more a skeptic rather than an optimist. So generally I believe that there is no life anywhere else. But my distinguished colleagues will throw more light on that because they know better than me. I am a hardcore technologist, so I will not know about the nuances of the astrophysics or astronomy. But generally, by intuition, I feel that there is no life anywhere else. So once NASA chief was here, and before that, everybody knows NASA, isn't it? Now, few people have started knowing ISRO also, especially after Chandrayaan 3. But hardly any people know about SAC, Space Application Center. And any of you know about SAC, Space Application Center? From students. So SAC, it is one of the centers of Indian Space Research Organization, ISRO only. So located very nearby from your place. That is in Ahmedabad only. Satellite area, what is known, it is known as satellite because of SAC. So Space Application Center is second biggest center of ISRO with around 2,000 employees there, regular employees, and we have another 1,500 contract people. So that way it is a very big center located in Ahmedabad. And as I said, it is one of the centers and one of the unique centers of ISRO because it does an activity which no other ISRO center does. It does a multidisciplinary activity, means we make sensors or instrumentation or payload. See, launch vehicle is one which goes to the space carrying the satellite. Satellite is the one which provides the platform. It provides you power and it protects you from many other things. But the actual thing which works, which does the work for 1 year, 3 years, 5, 7, 9, up to 15 years, is which is called the brain or the heart of the satellite, is the payload or the sensor or the instrumentation. And that instrumentation is built by our scientists here at SAC. So that way SAC has a unique place. Although it is not given that due credit, but the one thing which works in satellite for years together is the payload, and that payload is done at Ahmedabad Space Application Center. So that is one part. And then as is the motto of our space program, that we are doing all this for some end goal, isn't it? End product. This end product is applications. Why we do all this satellite-based research and all? It is for applications. So that applications is also done by Space Application Center. So that way it is a very unique center, that we make the hardware also and we do the software part of it also. Finally, it has to be put to use for doing communication, for remote sensing, for navigation like GPS. So all these activities also are being performed at Space Application Center. And then we hand it over to the actual users. So in that sense, it is a very unique center of ISRO. So, and it is also second biggest, as I told you. So please do visit SAC whenever you get the opportunity. So I welcome all of you. You can approach through your school principal or school management. So we'll arrange, already we have arranged many things for various schools. So we have a very good exhibition just outside our campus. So that is open even on Saturday and Sunday also. So please do visit that first, and then we can think of visiting inside also. So that is SAC. So as I was mentioning, very few people know about SAC. So that is one idea for doing all this program, is to make you aware about the activities which happen nearby your place also. So SAC is that place where space related, and of course PRL is also there, Physical Research Laboratory. And PRL is known for, and all of you know, India's father of space program is Dr. Vikram Sarabhai. And incidentally, he belonged to Ahmedabad only. So that way also we have a unique place in that. PRL and SAC, they were all founded by Dr. Vikram Sarabhai. And he gave the vision for India's space program, that we want to use space research and technology for the benefit of common man and society. That is what we do at SAC, as well as PRL. We do various advanced research activity related to astrophysics. Astronomy is one part of that, and many other things, which Dr. Ganesh will tell you more about that, so I will not dwell upon. But since the space program originated from this place, that is Ahmedabad, it is our duty that we see that what is happening here. So I welcome all of you to visit either SAC or PRL. PRL is arranging, I think, on 12th August, a open house also. So if some of you can get opportunity to visit that, that also take advantage of that. So Sarabhai told, as I mentioned, told us to use space for various applications which will benefit the common man in society. And afterwards he said something which generally I don't tell to the audience, because those days in early 70s or late 60s, his statement was that we are not here to compete with advanced countries to go to moon or Mars or put man in space. And we are celebrating Chandrayaan. So many of you will question us that what Sarabhai said don't do, we are doing that only. We are doing Chandrayaan, Mangalyaan, now we are going to do Gaganyaan and many other things, which my colleagues will be telling you about today, what all is stored after Chandrayaan 3. So it appears that in media or newspapers and everywhere you see that ISRO is doing only Chandrayaan, Mangalyaan or Gaganyaan and this sort of thing. These are all technology development. So this is one part of our activity. It is only 20% of activity which ISRO does. Rest 80% of it is something else, which I mentioned about communication, navigation, or remote sensing with optical camera systems or radar systems. So that is the real work which we do, which will directly benefit you people or all of us. So ISRO is something different from what is visible to you through media. But this is also a very important activity. Although Sarabhai, when he started our space program, he meant that that should not be our priority, because we have to, India is not that rich country. So we have to use our resources in an optimum way. So from that angle only he said that. But nobody gives this technology to you on platter, isn't it? Everything we have to learn in our hard way. We have to be Atmanirbhar. आजकल जो बात चल रही है ना, Atmanirbhar Bharat. So we want to be Atmanirbhar in technology. So for that we have to do Mangalyaan also, we have to do Chandrayaan also, Gaganyaan also, which we are going to do. Then we are going to have now our Bharat Antariksh Station. All of you have heard about ISS, International Space Station. Sunita Williams is right now stranded in ISS. So something similar space station India also wants to build after we do this Gaganyaan program. So next in the pipeline is, we have already completed Chandrayaan 3. Now we are going to do a collaborative project with Japan, which is called LUPEX, Lunar Polar Experiment. Chandrayaan 3 went up to 70-degree latitude near South Pole, but it was not exactly South Pole. Now we'll be going exactly on South Pole, 90-degree, with this LUPEX mission, which is the collaborative mission with Japan, where we will exactly go up to 90-degree, and that is more hazardous compared to what we landed here at Chandrayaan 3. Of course, this was also a very hazardous place. And then after that, we'll have or during similar times, we'll have Chandrayaan 4 mission, where you would have heard read in newspaper also that India wants to bring soil samples or rock samples from moon for here people to study that. PRL already has that samples which were received from USA, what NASA brought it. So some of the samples they've given to PRL also, where they're doing research on that. What is there in that soil samples or rock samples? So something similar India wants to do, bring our own samples from moon. So that is Chandrayaan 4. Then we have Mars landing mission. Last time when we went to Mars, we put an orbiter or a satellite around Mars. But this time we'll be landing on Mars. So you saw Chandrayaan 3 landing. Can anybody tell me Mars landing is easier or difficult compared to Chandrayaan landing? Can any student tell me? Generally you will feel that it is difficult, isn't it? But it is simpler compared to landing on moon. It is difficult to land on moon compared to landing on Mars, because there is a thin atmosphere on Mars. But the problem is Mars is very far off compared to moon. Moon we went in 41 days, although countries like USA, Japan or China or America will go there within 4 days. So why that also you can ask our scientists, why it is so, that they take 4 days to go to moon while we take 40 days. So there are also reasons for that. So as I was mentioning, landing on Mars is easier, but the problem is it is so far off. If I send a command right now, it takes 15 minutes to reach there, and then execute, and then give me back the status another 15 minutes. So after 30 minutes, I will know what I wanted to do has happened or not in that satellite. So these are all the difficulties. So these are challenges we'll be going to handle in the Mars landing mission. So like that, and Gaganyaan, of course, is going on parallelly. We are going to put man in space in due course within a couple of years, where man will be orbiting at a 400-kilometer height, and he will be there for minimum 1 to maximum 7 days, and come back on the Earth very safe. So we are right now trying to, we have all technologies, but we are trying to improve the safety factor. Because till now we were not there is no human life involved in any of our mission. But this for the first time human life will be involved. So that's a different dimension to the problem which we face. So all these things are going on, but as again I would like to emphasize, these are only the 20% of activity which ISRO does. Rest 80% of something is totally different things which help all of us directly. So please do visit our exhibition, visit SAC, so you'll come to know more about all these activities, which are important elements of our life. So once again, I thank IIT Gandhinagar and organizing team for organizing this event that will give you insight into all this aspect. Of course, you'll know more about Chandrayaan 3 landing, how it happened and how it was planned out, and what are the other future elements of that. And surely your understanding of science and other associated technology elements will improve with this exposure. So I wish you all the best to all the students who are participating in that. And once again, thank all the speakers for sparing their time and helping us in organizing this event. Thank you.
Thank you very much, sir, for this insightful message and those inspiring words. You have definitely kindled the urge to know more about SAC ISRO in the students. Well, I see a lot of curious faces out there. This is exactly what these events are all about, sparking curiosity and inspiration. Well, with this, I would like to thank our esteemed guests for gracing the stage with their presence during this inaugural segment. As we now proceed with the first talk, which promises to be both enlightening and inspiring, I request you all to kindly occupy your designated seats. Our first speaker for the day is Shri Pradeep Soni, a leading scientist at SAC ISRO, who will be taking us through India's incredible journey in space exploration with a focus on the Chandrayaan 3 mission. Shri Soni has been involved in the design and development of electronic subsystems for Earth observation and scientific payloads of ISRO, namely OceanSat 3, Cartosat 3, Chandrayaan 1, 2, 3, etc. He played an important role in Chandrayaan 3 as project manager for the design and development of lander imagers and rover imager. He played a major role in the payload electronics development as Deputy Project Director of OceanSat 3. He has been awarded with the ISRO Team Excellence Award in 2016. He is also the recipient of the prestigious IETE B.V. Baliga Memorial Award for 2023. Currently, he is the Deputy Project Director of Payloads for India's first space docking experiment. This talk is titled, A Rich Legacy and a Brilliant Future. This is going to be an exciting session where we learn how India's space missions are shaping the future. Please join me in welcoming Shri Pradeep Soni with a big round of applause. Hello.
Hello, hello. ठीक है, वो तो माउस से हो जाएगा. This one. Give it to me.
So we will notify you before the end of 5 minutes.
Okay. So, respected Director SAC, organizing committee members, and dear friends, very good morning to you all. Today, I would be taking you through the journey of India's space exploration program, and also I would be speaking specifically about India's programs to the Chandrayaan. So, India's journey to the moon began with Chandrayaan 1 in 2008 when we launched our mission, which was purely an orbiter mission. Subsequently, Chandrayaan 2 was launched, which was a combination of orbiter as well as lander. And in 2023, last year, we also completed our Chandrayaan 3 mission, which was purely a landing mission. But before I further go into details, let us all revisit that moment of glory. And let us watch this video once again. So this video is the historic, lift-off of the Chandrayaan 3 and the touchdown of the lander mission.
1, 0.
So this is the lift-off. This GSLV Mark 3 carrying Chandrayaan 3, soaring high into the sky. And now the D-Day, when the lander successfully landed on the moon's surface. So the day was 23rd of August. And that's the touchdown. And that's the moon control center.
India is on the moon.
That was the final declaration, and that's moved across the country. So actually, I showed this video just because actually this event was live stream on the YouTube, and till date, this event was I think it is the most viewed live event in the history of the YouTube. So that was the impact of the Chandrayaan 3. Thank you. Now, a little bit of history. As sir has already pointed out that Dr. Vikram Sarabhai is known as the father of India's space program. He always emphasized the fact that we must be second to none in terms of utilizing space technology or embracing space technology for the benefit of common man and society. So with this vision and because of his great efforts, the INCOSPAR was set up. So INCOSPAR was the first official body, which was dedicated for the space research, and that was established by the then Prime Minister Pandit Jawaharlal Nehru in 1962. Subsequently, TULS was established, which was the Thumba Equatorial Rocket Launching Station. Basically, it was a launch pad for the sounding rocket launch in 1963. And then first lab was set up in a small church. So basically, one small church was used as a rocket assembly component and testing, etc. So this, you can see this, Here we can see the church, that St. Mary's Magdalene Church was there. So where the all ISRO's first lab, this church was there. And then the first sounding rocket was launched in 21st November 1963. So which began the India's rocket science program. And 1969, the INCOSPAR was reconstituted as ISRO. And in June 1972, which also marked the 25th year of independence, the ISRO, basically a separate space commission was formed and Department of Space separately was formed. And ISRO was brought officially under DOS, which was initially under Department of Atomic Energy. In 1972, it was brought under the DOS. Now, for any space missions to be operational, we always need a satellite. We always need a payload, which should be orbiting around certain orbit. And we also need a launch vehicle, which should carry this spacecraft or the satellite into the space. For that vision, India started its satellite launch vehicle program, known as the SLV. And the first launch, successful launch, happened in 1980 when it carried Roni satellite in its 400-kilometer orbit. So that began India's journey to the space, and it put India in the map of few spacefaring countries, which has the facility of satellite building and launching facility both. So some of the images we can see here, these images are very iconic in terms of their importance. In the first image, we can see Dr. Vikram Sarabhai is in discussion with another visionary, is none other than Dr. APJ Abdul Kalam. And the bottom side, we can see the iconic images of first launch of SLV-3 and sounding rocket, etc. Now coming to the ISRO's growth, starting from a very humble beginning, starting from a lab in a church, ISRO has presence in all across the country. So there are 21 centers or labs are spread across the country, which are dedicated for different space activities. Some of the prominent centers I'm showing here. The first image is of VSSC. VSSC is the largest ISRO entity which is dedicated for the space launch vehicle development, design and development activities. Then ISU Trivandrum is for the scan mechanism and similar, many inertial system development activities. URSC Bangalore is there for the mission planning, project planning, and satellite component development. SAC Ahmedabad, which is located in our city, is the lead center of ISRO, which is dedicated for the development of payloads and its application, as Sir has already mentioned. Then IPRC Mahendragiri and LPSC Trivandrum. These two centers are dedicated for the liquid propulsion systems development, design and development. SDSC SHAR, you would have seen that a lot of satellites are launched through this satellite. So this is the only launch pad of ISRO from where the satellites are launched into the space. Then HSFC, the Human Space Flight Center, is also there in the Bangalore. And NRSC Hyderabad is the lead center for the remote sensing data product generation, and IRS Dehradun is for the advanced scientific research on the remote sensing. So these are some of the prominent centers for ISRO. Now coming to the SAC, Ahmedabad, which is located in our city itself. So SAC is a very leading center in terms of satellite, the payload development for all satellites and its application development. Those satellites or the payloads can be broadly categorized as communication, navigation, and Earth observation payloads. Apart from their satellite payload development, SAC is also involved in development of its application pertaining to communication, navigation, and remote sensing. Apart from these operational missions, SAC is also providing payloads for the many science and experimental missions like mission to Moon, mission to Mars, Aditya L1, and recently we are also providing payloads for the SPADX, that is a space docking experiments. Now coming to our SAC main campus, it consists of various units. The main campus is in the Satellite Road, Ahmedabad, which is spread across 90 acres of lush green campus. Then New Bhopal campus is there for the navigation and communication payload integration and assembly activities. Then Delhi Earth Station is there in the Delhi, which is part of the SAC for the data reception. And in space technical complex is situated in Bhopal, and also Bhopal Technical Campus is another center. So all these entities are coming under the SAC. So these many centers are already Sir pointed out. You should visit once just to have a look at it. Now coming to the India's space odyssey, ISRO has come a long way, and so far it has completed 124 spacecraft missions, and 96 launch missions have been completed, and soon we will be touching the century for the launch. One Gaganyaan mission has been completed, and around more than 400 satellites have been launched for the foreign countries by ISRO. Around 17 satellites have been realized by private players or the students, and 8 re-entry missions and poems have been launched. So these re-entry missions becomes very critical when we talk about sending humans into the space, and that's why we are also gradually mastering this re-entry missions. And poem is another innovative experiment thought of by ISRO scientists, that the PSLV, the fourth stage of the PSLV, which releases the payload finally. This fourth stage can be used for the many other space applications or explorations, because it remains in the space for a few duration. Now coming to the space applications, so the data we receive from the satellite has vast number of applications, and some of the applications actually these applications pertains to communication, navigation, and the remote sensing. Some of the communication satellites applications are rural connectivity, remote internet connectivity, mobile connectivity, etc. Then telemedicine, teleeducation, another sector which where the satellite communication satellites provide their data. Then some of the navigation data are used in civil aviation, spin-offs, for logistic services, e-commerce websites. These use GPS or the Navic facility for their day-to-day activity. Then remote sensing data provides national asset directory, resource management, and also they help in identification and protection of the heritage sites. Now, in the last 54 eventful years, ISRO has grown by leaps and bounds. So we have a full family of satellites, whether they are communication, meteorology, navigation, Earth observation or planetary exploration. We have full-fledged family of the launch vehicles, including PSLV, GSLV, and also we are gradually mastering re-entry technology. So ISRO, rather than India, is one of the few countries who is self-reliant in terms of satellite building and launching. So ISRO is not just an organization, it's a winning team. Now coming to the ISRO's launch vehicle family, as I already mentioned, it started with the SLV-3, then it grown up to ASLV, Advanced SLV, then PSLV, GSLV. GSLV Mark III is the heaviest launch vehicle for the ISRO, and in future, recently we will be, soon we will be launching SSLV also, which will be the newest entrant in the family of the launch vehicle, and in future we will be building launch vehicles for the human space, related activities, and also for the next generation launch vehicles are also in pipeline. So basically these launch vehicles, provide different weight categories of launch, and at the launch at the different height of the orbit. Now this shows the evolution of Indian satellites. We can see all sorts of satellites, a large number of plethora of satellites are there. Some satellites are still functioning. So we have full, satellites group constellation working for the different applications, whether this Earth observations, NAVIC communication, or lunar missions. Here we can see the NAVIC. NAVIC is similar to the GPS, so we provide our GPS-like facilities or services, and we can see IRNS series have full constellation which is providing those services. Now, coming to the moon. Actually, usual question is why we want to explore the moon. So before, answering this question, let us understand the evolution of the moon. So in this
no
video,
one is certain
basically it's an
how
animation.
this charcoal black and snow white celestial companion of Earth was formed.
The evolution of the moon has been explained, how it has been formed. So we can see in the early days when Earth was the only single body, celestial body, impacting by an asteroid, certain fragments, got this.
The most likely
from the
theory
Earth,
is that a
and in due course of
Mars-sized
time,
planetary body traveling at high
they
speed
formed the moon.
collided with the young Earth. The molten material from the two bodies eventually formed the moon.
So as we can see, the moon formation is, from the basic constituents of Earth only. So the study of the moon provides the early evolution of Earth. So that is one major reason to go for the moon. And also many satellites, many missions have corroborated that there are plenty of resources, minerals available, including the water on the moon. So that is another reason. But the biggest reason is that it is the only natural satellite of Earth. So it's the closest celestial body to our Earth. So it's obvious to, go into and do some of the research. And it's basically it orbits around, Earth in a elliptical orbit. So its distance from Earth during the perigee. Perigee means the closest point with respect to Earth is 3.63 lakhs kilometer, while in the case of apogee is the farthest point with respect to the Earth, is around 4.05 lakhs. So average distance from the Earth is around 3.84 lakhs kilometer. And some of the physical parameters of the moon, radius, surface area, volume. So it's a very small object comparable to Earth, and because of its less mass and density, its gravitational pull is around 1/6 of that of the Earth. So we can see acceleration due to gravity is 1.62 meter per square second, while that of Earth is around 9.8 meter per square second. So any object which is having certain weight on Earth will be lighter by 1/6 in the moon. That is the basic science. Now coming to the moon landing missions. So moon landing missions initiated basically when space war was going on, space race was going on between earlier USSR and USA. Russia was pioneer in terms of landing missions. So it initiated lunar missions for the soft landing on the moon. And the first mission which landed successfully on the moon was Lunar 9. That happened in 1966. But in due course of time, NASA took over that race, and it won when it placed man on the moon. And that happened on the 20th July 1969 when 3 astronauts on board Apollo 11 landed on the moon surface. So here we can see lunar module Eagle is shown here, through which they landed on the moon. And in the picture you can see Neil Armstrong, and the second picture is of Buzz Aldrin taken by Neil Armstrong. Now in the moon's surface, the newest entrant was India when it landed its Chandrayaan 3 mission in 2023. Now coming to the summary of total moon landing sites, we can see these, basically we have two sides of the moon, near side and far side. Near side of the moon is that which is always visible to us from the Earth, and the far side is the opposite side. So we can see all the landing sites have been in the either northern region of the moon or the equatorial region of the moon. The reason is that these areas are free or safe to landing. They are free from treacherous terrains or boulders or craters. So it's basically thought of rather safe to landing. India is the first country, India was the first country to land on the southern region. We can see the blue dot, so which shows that, which is very difficult to land because it's full of boulders, craters and terrains. Other side of the moon is also having similar situation. They are very tough to land, and the China is the only country who has reached that side. So this is the summary of landing missions. Now coming to India's journey of Chandrayaan. So it started with Chandrayaan 1. So when India declared in 2004 or 5, when the then Prime Minister Atal Bihari Vajpayee gave an approval for the Chandrayaan mission, then when it declared that it is going to be on the moon, many space country, faring countries or space agencies came together to work in collaboration with India, and many payloads were provided by different space agencies. So out of 11 to 12 instruments, around 5 to 6 instruments were from the other space agencies. So in short, it was not only India's first mission, it was a kind of an international mission after a long gap of time. So that was launched in Chandrayaan, it was launched in 22nd October 2008 by PSLV CL-1 flight, and it achieved its lunar orbit insertion in 12th November 2008, approximately 20 days afterwards. And the biggest, one interesting event happened in this mission. Actually, one instrument was their moon impact probe, and through this impact probe, India placed its flag on the moon first time. Because this moon, actually because of the thought of, or the vision of APJ Abdul Kalam, he proposed the idea that whenever we are going to the moon, we should place our flag onto the moon. So what happened, the moon impact probe was painted by the Indian flag color, and then upon releasing, it impacted on the, it impacted on the lunar surface, India's flag presence was there. So that impact happened on 14th November 2008. So since it was the birthday of the Pandit Jawaharlal Nehru, our first Prime Minister, so that impact point was named in the honor of him, and that point is called Jawahar Point. And since it is orbiter mission, it achieved a 100-kilometer orbit. The launch weight was around 1400 kg, and it carried out remote sensing, imaging of the moon in various bands, visible, NIR, that is near infrared band, and X-ray regions. But the biggest discovery of this Chandrayaan 1 was the discovery of the water. So the moon mineralogical mapper, or the M-Cube, that instrument was from the JPL NASA, that discovered the presence of water on the moon in 2009. So that was the biggest achievement of Chandrayaan 1, and it also provided the first mineralogical map of the lunar surface through the data of various imaging instruments like TMC, HI-SEAS, and also some other X-ray instruments. Now coming to the Chandrayaan 2. Chandrayaan 2 was an augmented mission of Chandrayaan 1. While Chandrayaan 1 was purely orbiter, Chandrayaan 2 was an augmented mission including lander and rover. The lander was named in the honor of Vikram Sarabhai as Vikram lander, and the rover was named as Pragyan. Pragyan is basically Sanskrit word for the insight. So it was supposed to provide some new insights, that's why it's named Pragyan. Now one interesting story I would like to share which is associated with Chandrayaan 2. When Chandrayaan 2 project was conceived, it was in the joint collaboration with Russia. India was supposed to provide the orbiter, while Russia was supposed to provide a lander and the rover. But due to some reasons, Russia backed out. Some technical reason maybe, I don't know, but they backed out. And that's when ISRO was left alone in its lander and rover development. But it was a blessing in disguise, and in due course of time, we developed our own lander and rover. And that's why it took a bit long time, and it was launched in 22nd July 19 after 11 years of gap. But some of the major achievements of this mission were successful translunar injection. In our successive event towards moon, we achieved this success, which is very critical event. Then separation of lander and orbiter is another critical event which we successfully done. Then deorbiting, basically the reduction of the orbit of lander and site identification for the landing was also successfully achieved, and successful descent phase in rough braking. Rough braking basically is the it's a reduction in the very high speed of the lander, so that also was successfully achieved. But unfortunately, lander communication lost in last before touchdown, within the last 2 kilometers, our communication lost with the lander, and unfortunately it crash landed. But apart from that, all the mission stages for the landing were quite successful. And orbiter is still having 8 instruments on the moon, which are still orbiting around the around the moon. And one of the payload is OHRC. OHRC is the one of the payload that is orbital high resolution camera, and this instrument provides the highest resolution images of moon in the world. The second best resolution is having of LRO. The OHRC resolution is 0.3 meter per pixel, while LRO resolution is 0.5 meter per pixel. So we can see now this clarity is depicted in these two figures. In these two figures, we can see the landing sites of the Apollo 11 and Apollo 12 mission. In the left side picture, the Apollo 12 landing site is shown here, where the intrepid decision stage is clearly seen, and similarly here the moon-bound maneuvers are carried out. So opposite to that of the earth-bound maneuvers, moon-bound maneuvers are carried out to reduce its orbit from large elliptical orbits to the circular orbit of 100 kilometer. Then PM and LM, that propulsion module and lander module are separated. So when they achieved 100 kilometer circular orbit, at one point the separation is happening. PM or the propulsion module keeps on orbiting around the moon, but lander immediately after deboosting. And deboosting means its orbit is reduced to 30 kilometer, and from that point the actual landing begins. So here the landing trajectory has been shown. You can see from 30 kilometer the rough braking phase starts. In this rough braking phase, what happens? The lander is traversing with a very high horizontal velocity, that's around 1.68 kilometer per second. So that velocity is reduced to 358 meter per second. In this case, what happens? The thrusters are mounted on the bottom side of the lander, and those are fired. And upon firing, those thrusters provide the the thrust in the opposite direction of the velocity vector. So that is how this velocity is reduced. Then the next stage is attitude hold phase. In this case, what happens? The landing site determination is happening. In that case, LPDC or the lander position detection camera is activated, and it is identifying the landing sites. So basically, this identification is happening by continuously capturing of the landing, landing sites or moon sites of the images, and then those images are continuously compared with the internally stored libraries, and that identify or finalizes the landing site. Then we start the fine braking phase. At the end of fine braking phase, the lander literally becomes still without any horizontal and vertical velocity. At the height of 1.3 kilometer, it literally starts floating or the hovering. This is called the hovering phase. And from this phase, start the activation of the LHDC, that is the lander hazard detection camera. And basically, it sees is there any hazards or there or not. So basically, it detects if there any craters are there or boulders are there or any kind of sharp edge it detects and avoids so that it cannot topple upon landing. So this is hovering, and then gradually starts descending towards the moon surface, and you can see some alternate red color trajectory also shown. In case of any hazard is detected, it will automatically move towards some other place for the safe landing, safe landing. But fortunately, it was a textbook landing, and without any alteration in the landing site, it was successfully landed on the 23rd of August 2023. So these are the summary of the sensor which helped lander to land. So some of the inclinometers were there. Inclinometer were providing the inclination of the lander. Then carband and laser altimeter were there for the determination of the altitude. Then lander position detection camera for the identification of landing sites. Then lander horizontal velocimeter and lander Doppler velocimeter. Basically, these velocimeters are to determine the horizontal and vertical velocities. Then LSDAC, the lander hazard detection avoidance camera, was there to detect any kind of hazard and avoid it. Then star sensors were there to orient the lander's orientation. Then lander imagers, 4 units of lander imagers were there, 2 main and 2 redundant. And personally, I was involved in development of lander imagers, and you would have seen that many images were continuously flashed on the screen when it was landing. So those all images were taken by the lander imagers. And one rover imager was also there. You can see in the rover, one boxed area is there. So that is the location of the rover imager, and it was supposed to take certain images of the moon surface when the rover was traversing. So this figure shows the various imagers and sensors mounting locations. So we'll skip that. Now, apart from these imagers and sensors, Chandrayaan 3 also carried payloads. Payload means some of the instrument which provide scientific data to scientific community. So lander payload has 3 payloads: Ramba, Langmuir probe, Chastity, and ILSA. Ramba Langmuir probe was discovering or doing research about the Earth's plasma and its variation with respect to time. Chastity was Chandra's thermal to take the thermal profile of the moon surface. ILSA was to sense some of the seismic activities on the moon surface. 2 payloads were there on the rover, apex and LIPS. Those were the some X-ray region spectroscopy for different minerals detection, and then propulsion module carried 1 payload named Shape. So when orbiting around the moon, this was capturing the images of the Earth in some IR region. So all those payloads are still operational basically. Now coming to the SAC contribution in Chandrayaan 3 mission. SAC provided, as I already mentioned, the 4 lander images. I already mentioned 4 lander images, 2 main and 2 redundant, 1 lander position detection camera, 1 rover imager, 2 lander hazard detection avoidance camera, and then Kara altimeter and its digital processor shown in the bottom electronics card. So this is the Kara radar altimeter. And in the right side, you can see that algorithm which helped lander to land safely on the moon surface. So that full algorithm was developed and in the SAC DP team, and that algorithm software, it was a software which was implemented in the hardware. That DP or the processing card you can see in that hardware, this was implemented. So you can see SAC has played a very vital role in the landing.
Liftoff will start in T-minus 10 seconds.
Basically, this is an animation how this Chandrayaan mission accomplished. So right from the launch and its various earthbound phases to moonbound phases, it will be showing, which I already just explained. So I will be scanning it fast. So this is the liftoff.
6, 5, 4, 3, 2, 1. We have ignition.
So this is the separation of this strap-on booster, which are the solid propellant-fueled boosters. Then after the launch vehicle has crossed the atmosphere, the heat shield are separated. Then the liquid stage will be separated. This is the liquid stage. And once those fuels are consumed, those stages are continuously separated. Now the third stage, which is the cryo stage, will be separated, and lander plus propulsion module will be on its way to the moon. And now these are the solar, and yeah, this is the earthbound maneuvers in which the orbit raising activities are carried out. So 5 to 6 such maneuvers are carried out. You can see that. And once the desired thrust is achieved, it will traverse to the moon. So that is the lunar transfer trajectory. And this is the successful lunar orbiter insertion. Now once the circular orbit is achieved, the PM and LM separation will happen. So that is where the lander and propulsion modules are separated. And lander will reduce its orbit to 30 kilometers. So now it started its journey towards moon surface. Now we started the scanning of the landing sites. The continuous various sensors images are activated. These are the site identification, and you can see the thrusters which are continuously fired to control the speed, and in a controlled descent it successfully lands on the moon. So after the successful landing, now this is the another video in which the actual pictures taken by the lander images have been shown, and one interesting experiment which we carried out will also be shown here. We did what was that when the leftover fuel was available, we again lifted the lander. So that event we will be showing here. So this is the images of lander imager. You can see the panel, some of the portion of the panel is also visible. So, and the moon surface is continuously scanning. So it was a live video feed we were getting from this lander imager. as it is descending towards the moon surface, you can see, the craters are getting bigger and bigger. That is how we are getting close to the moon surface. Yeah, and after successful landing, in this video, rover deployment. In this case, we can see the ramp on which the rover was attached. It is deployed, and the rover will be, taken out, and it will deploy its solar panel to get energy from this sun. So here we can see right now the solar panel is in stove condition, and it will be deployed in few moments. Yeah, this is the solar panel now deployed of the rover. Now rover will start, descending from the panel. This is the hop experiment, in which you will be seeing the hop. Means basically when the thrusters are fired, the moon dust, flew, and you can see this is the firing of thrusters. It lifted the lander around 40 centimeters above the earth, and then it landed and settled into the same place. So basically, two experiments. One was this hop experiment, and another interesting experiment which I will be discussing in a sequence. So these additional to these, landing and rover movement, additional two experiments were carried out. One was this hop experiment. Now, one of the very great or iconic images are that when rover, ejected from the lander, after a movement in some, distance, it turned back towards the lander and it took picture of the lander. So in this picture, you can see how, lander is standing, and in this circle, you can see the two instruments. One is this Chastity probe, which is inserting into the moon surface, and the ILSA, which is doing in situ experiments on the moon surface. So that is one of the great few pictures. And this is the rover, movement. And these are some of the tracks which are left by the rover movement. And this is the images showing that, pre-landing image by OHRC, that is our orbiter high resolution camera, which is our biggest, highest resolution camera. Here we can see clearly its shiny object with its shadow. So this is before and after landing. And these are the images from the dual frequencies. This is the radar imager, in which we can see before landing there is no shine, and after landing this shiny object is the presence of the lander. Now, our lander was also, verified by various space agencies from the, other countries, like Davari from South Korea, whose resolution is around 2.5 meter per pixel. It detected the presence of lander here. And the LRO, the Lunar Reconnaissance Orbiter from NASA, whose resolution is around 50 or 0.5 meter per pixel. So it detected the presence of lander. But the best image from our OHRC, here we can see its shadow as well as the shiny rectangular portion. So that, that is the clarity of our own OHRC. Now these are some of the scientific instruments results. This Chastity provided thermal profile of the moon surface, and these are the LIBS data which confirms the presence of sulfur on the moon surface, and the APEX discovered the presence of minor elements like some of the minerals, and these are the Rambha-Langmuir probes. So all scientific payloads are providing their data successfully, and this is the seismic activity detected by the ILSA instrument. And in this figure, we can see the shadow of this Langmuir probe, which was deployed after the landing. Now the second experiment, which was carried out additionally from the intended, was the retrieval of the propulsion module. Initially, propulsion module was orbiting around the moon, but 100 kg fuel was left. So what we thought is that we should take it back. That will help the understanding how a return mission can be taken place. So that propulsion module was retrieved in its Earth orbit, and currently it has been retrieved from the lunar orbit to the Earth orbit, and now it is orbiting around the Earth at around orbit of 1,54,000 kilometers. So that was another added experiment which was successful. Now, in future, Chandrayaan 4, as Desai sir already mentioned, that in future we are planning to take lunar sample back from its soil, its surface. So that will be the next Chandrayaan 4 mission, in which the soft landing everything will be same, but after soft landing, the descent on the moon surface, the collection of the sample will be there, and to transfer that sample, docking will also be experimented. So that's why docking is another very important experiment which is going to happen in future. So basically that is another project which is next in pipeline. So lunar sample will be collected and taken back to the Earth. And this slide shows the future roadmap of space exploration, in which we can see after Chandrayaan 3, the next mission prior to Chandrayaan 4 is the SpaceX, which will be successfully experimenting the space docking activity, because Chandrayaan 4 will consist of docking also. So before Chandrayaan 4, the docking will be.
Feel free to discuss any more questions.
Any school kids specifically?
Sir, the dust part of the left satellite is the running on the space. So in the future, the next satellite is launched. So he will crash due to his.
Speak louder because I'm not.
The left part of the satellite at this time is run on the space. And
Left satellite?
Yes, left part of the satellite is running on the orbit of the Earth. So
Yeah.
in future, we launched the next satellite. So is crashed due to the some parts.
Acha, you want to ask the remaining of the satellite,
Yes, remaining part of the
whether
satellite.
they are posing any threat to the
Yes.
future. Yes, it is there, because all countries are launching their own satellites. So basically, indirectly, it is creating a kind of a space debris. But the thing is that there is a space debris management units are there. They have their own satellites to manage those debris. And when the satellite is launched, prior to launch, this debris is always detected, that in the path of this launch, whether any object is coming or not. So that is already, studies going on. But yes, this is a very, I think, what we call a serious issue in future, not right now, but in future, this is going to be a serious issue. Right now, we have sorts of mechanism in which we can avoid right now. So, I mean, before launching, those things are taken care.
Thank you, sir.
What is the purpose of Chandrayaan 4?
Chandrayaan 4 already I think mentioned, in which we will be collecting samples from the moon surface, and we will be taking it back for its study. So basically, it's not only just sample collection. You can see all Chandrayaan missions provide the opportunity to do advancements in technologies. Like in this Chandrayaan 3, we experimented successfully the landing mission. Now this next will be Chandrayaan 4, and will be collecting the sample is one thing, but before that we have to dock it so that the orbiter instrument can collect the samples. Then again re-entry experiments which are very critical. So those sorts of new experiments to be validated in Chandrayaan 4.
What kind of research?
Research means, say, I already mentioned that the moon's constituents is similar to that of the Earth. So its study provides the insight into the early evolution of Earth. So those samples from the soil of moon will provide that kind of insight, and also the presence of minerals and all can also be corroborated in situ experiment. Like so far we are doing remote studies. We are sending orbiters, and because of their reflected radiance, we are getting certain signatures. But when we have the actual soil, we can do experiments on a better way. We can corroborate or validate the same thing.
Okay.
Thank you. Yes. Yes. Yes.
What are the cryogenic fluids, if you can give an insight?
Cryogenic, basically and if you understand, it's a very low temperature, So those, when we talk about solid and liquid propellants, they take certain mass and they have, their certain energy. But cryogenic is basically liquid oxygen and hydrogen in a very, they are compressed in a very low temperature. So in that temperature, these elements remain in liquid form. But these are the very best and efficient fuel, and they provide the desired thrust upon ignition. So that whatever thrust is required to launch those geostationary satellites or go to the GTO orbit, so that kind of thrust is only achieved through this cryotechnology. So that's why it is very important when we talk about the mission which is going deep high into the sky. For lower orbit, this fine, solid and liquid fuel will be sufficient. But for going into the higher, into the space, we need cryogenic technology.
Sir, there is a life possible on
Yeah, actually in the moon, as I already mentioned, no, we have explored the presence of water which can facilitate the life, but so far, no.
But sir, according to science, according to you, how many years it will take
How many years?
to make a life on the moon?
No, right now there is no life in any other external planet, right? We need to, learn how to habitat on these planets. Now we need to, for this habitation, we can utilize their resources, like we can utilize the presence of water and minerals, and we can form a kind of a station, base station, in which we can live. But making life is totally different. I mean, automatically there is no life right now. But only thing, we can explore the opportunities through which we can live, like in Mars. Also means, since Mars is similar to that of the Earth, environment is there. But still life is so far not been found there.
Okay, sir. So, sir, we will find some water on the moon. This water is pure or not? It is usable for us?
Yeah, for that only the instruments are, need in situ experiments. For that only the soil sample collection will be taken. And these are the frozen water so far, because if you see, the temperature on the polar region is very, very high. So mostly it is a frozen water. Purity and impurity I am not sure. But yes, certainly there is a H2O and hydroxyl presence is there, which can be used for water formation.
So, sir, how is possible to collect these resources and water from Earth, from moon to the Earth?
For that only, actually in earlier missions also, if you see one mission of Lunar 25 of Russia, they already did that. They have collected moon samples to the Earth also. Same way we are going to do it same. I already told you, sample collection is one thing, just to in situ study and physical experiments. But the thing is that we need to master some advanced technologies. So in future, of course, sample will be collected. There will be certain technologies like we will be having rover arm taking out the samples. Then it will taking out those samples in certain box or container. So that container will be transmitted to the orbiter. So all those technologies to be mastered before taking samples to the Earth.
But sir, it takes very long time.
Yes, it will take long time. Yes, we have to master this technology.
So due to time constraints,
what very good questions.
We can maybe take on more questions later. So our speaker sir will be here with us, and you can maybe chat with him during the break and discuss more. Please feel free to discuss more questions during the break with them. So thank you, Shri Soni, for that inspiring and insightful talk. I would request you to please give him a big round of applause. It's really amazing to see how far we have come and where we are headed to.
So next up we have Professor Gulab Dewangan from IIT Pune, who will dive into Astrosat, India's first space-based observatory. Professor Gulab Dewangan is a renowned astrophysicist at the Inter-University Center for Astronomy and Astrophysics in Pune. He has led several successful observing proposals in NASA, ESA, JAXA, and ISRO missions. At IIT, Professor Dewangan explores multi-wavelength science using India's Astrosat observatory, enhancing our understanding of celestial objects through UV and X-ray observations. He took up the challenge of realizing multi-wavelength science with the first Indian space observatory, Astrosat, and brought out several interesting results. Beyond his research, Professor Dewangan is dedicated to sharing knowledge and expertise, making the Astrosat mission accessible to the scientific community through workshops and training programs. This talk is titled Astrosat, India's efforts in space-based astronomical observations. So if you have ever wondered how we study the universe from space, then this session will give you all the answers. So please welcome Professor Dewangan.
Thank you very much, and very good morning to all of you. I'm very happy to come here and talking to you here, and thank you to Professor Anand Sengupta here for inviting me. Today I'm going to share some of the excitement with the multi-wavelength observations with India's first astronomy mission called Astrosat. You have heard a lot about Chandrayaan, but I'll be talking about another very important mission by ISRO, which is Astrosat. But before going into, before talking about the Astrosat, let's go through some of the basics, why we need space astronomy, and particularly why we need multi-wavelength astronomy mission. So when we look at the sky, because our eyes are sensitive to the optical light, when we look at this night sky, what we see is number of stars, mainly stars. You also see planets, etc. What you generally you see large number of objects. But if you use optical telescopes, you see numerous, much more fainter objects. And when we receive these lights from these numerous objects or different objects and study the light, analyze the light, and try to understand the internal working of those objects, then what we have is optical astronomy. Astronomy which uses visible radiation or optical radiation, that we call optical astronomy. Okay. So using, because our eyes are sensitive and our technology is, of course, very good with optical astronomy, optical detections. So until the 20th century, virtually all of the astronomical knowledge about cosmic sources came from optical astronomy. But visible radiation is only a very, very tiny fraction of the entire electromagnetic spectrum. Okay, for example, if you look at the electromagnetic spectrum, and when we say electromagnetic spectrum, essentially it consists of the electromagnetic waves at different wavelengths. What are these electromagnetic waves? These are essentially oscillating electric and magnetic fields which are propagated in space. And the electromagnetic waves are characterized by wavelength, so-called the wavelength. And what is wavelength? Wavelength is the distance between two identical points in these oscillations in the consecutive cycles. For example, you can think of the distance between the two crests in the which are consecutive. That is the wavelength. And when you look at this, the wavelength of different kinds of electromagnetic waves, they are different. They are not same. For example, in the case of radio waves, the wavelength is the longest. It can range from a few centimeters to several hundred meters. Okay, and of course, you know the application of radio waves. We use for our radio communication, our transmission of television signals, etc., using the radio waves. Then, if you go to slightly shorter wavelengths, these are microwave radiation, then infrared radiation, and then comes the visible part of the radiation, which our eyes are sensitive. And you know, the visible radiation only is, as I was mentioning, is a tiny fraction of this entire electromagnetic waveband. It ranges from something like 4,000 to 8,000 angstrom. Okay. Then the shorter wavelength, ultraviolet radiation below about 3,000 angstrom or so, and going up to about a few hundred or 100 angstrom. Then it begins the X-rays, which have even shorter, much shorter wavelength, and the size of the wavelength is the size of the atoms here. And then the shortest wavelength or the highest energy radiations are this gamma ray radiation. Of course, the wavelength is related with the frequency or also the energy of the photons. For example, for the radio waves, the longest wavelength radiation, the frequency is the shortest. While you come to ultraviolet, X-ray, and gamma ray, which are the short wavelength regime of this electromagnetic spectrum, they have highest frequency. Gamma rays have highest frequency or the highest energy. Okay. You can also think of the radiation in terms of temperature of something which emits the maximum at that particular wavelength. For example, you can imagine the sun. We see this yellow golden color of the sun, and that color is due to the radiation from the sun, which peaks in that particular band, around 6,000. Because of the temperature about 6,000 Kelvin, it peaks in that particular band, and we see the particular color of the sun. So here, now if you are talking about ultraviolet, X-rays, or gamma rays, for example, and visible when you are talking, it's about 5,000 Kelvin or so. So visible radiation, when we are receiving from an object, the temperature you can associate is about 5,000 Kelvin or so. Similarly, when you go to the ultraviolet, corresponding temperature will be something like 50,000 Kelvin or so. X-rays will come from a source which is very, very hot, million degree Kelvin, or tens of million degree Kelvin. And gamma rays even higher. You can associate with even higher temperature. So as I was mentioning, the visible band is very, very tiny fraction of this entire electromagnetic spectrum, which means that we are getting only a very limited information if you are only using the visible band for observation of cosmic sources. So we are actually missing a lot of information in that case. So you can associate this this thing with a story, which is actually an Indian story. So there were some, let's say, there are 5 blind men in a small village in India, and they were not familiar with the elephant, with this animal, elephant. Okay, one day this elephant walks into the village, and the blind men happen to hear the voice. Of course, they cannot see. So happen to hear the voice as well as they smell, and they try to they have puzzled, what kind of animal is it? What kind of thing is this? So one of the blind men touches the trunk of the elephant and looks, okay, this is roundy, somewhat long, and this kind of a wiggly. So it's like a snack. Okay, another one. And you can imagine, okay, if you're observing at one wavelength, we are having one particular information you can see. Okay. Then another blind man, of course, touches the ear of the phone, and that's it. Okay, this is it has some size, it's a thin, it can actually move, so it's like a fan. Another one touches the body, the main body of the elephant, and looks like it's a void, its size is large, and it's a kind of a hard, so it's like a wall. The another one touches the tail and says, oh, it's a thin, long, it's like a rope. And the 5th blind man touches the feet of the elephant and says, well, it's a strong, it has a rough patches kind of thing, so it's like a tree. So you see, individual blind men, by examining one part of this entire animal, are not getting the right picture. So same thing can happen in when you are using limited information, and when you combine all of this, you get this kind of a picture. Of course, it is completely misleading. Of course, in astronomy, the situation is not that bad. Even if we are using a single band, we do get a pretty much accurate information, but it is limited. We do not get the full information. We miss a lot of information, and that is why we need multi-wavelength astrophysics. And to give an example of a cosmic source, a very famous cosmic source, which is the Crab Nebula, how does it look in different wave bands? And what kind of information we get from these wave bands, different wave bands? Let's go through this. So first of all, what is this Crab Nebula? This nebula is the remains of a star that went through supernova explosion a long time back in the year 1054. So what really happens, if you think of a massive star, the star, of course, is shining due to the nuclear reactions in the core. And when the fuel in the core, when it ends, then it cannot really support the gravitational infall of the material. So what happens? The core of the star actually contracts, and depending on the mass of the star, it actually forms a neutron star with a size of only about 10 kilometers, and the density is very high, similar to the density of nuclear matter. And when it forms the neutron star, when it collapses, there is a huge amount of energy released. That energy actually blasts away the surface layers of the star. And those surface layers are, when they are ejected, and that's when it becomes, we call it a supernova explosion. And you see this, the surface layers which are thrown out in the form of a nebula. The neutron star which form, that is rotating very fast. In this particular case, we call this crab, neutron star in the crab, which is rotating 30 times per second. It also has a very strong magnetic field. When a highly magnetized object, when it rotates very fast, it can actually fuse highly energetic particles, which can then, when they are moving in magnetic field, they can also give rise to the synchrotron radiation. So here, these filamentary structures are the remains of the star which were thrown out. Then you also see some kind of a diffuse emission, and that is due to the electrons moving in the magnetic fields, and they are emitting in this particular band. So here are the pictures of the same object in different bands. in the radio band, you see a white dot. That is the neutron star, which is rotating very fast, and we call such a neutron star a pulsar. Okay, and then there are this diffuse kind of emission, and that is the emission of the electrons which are moving in this magnetic field, and we call this process as the synchrotron radiation. These are the synchrotron radio emission observed in the radio band. Okay, when you look into the image taken in the infrared, what you see here, there are some red filamentary structure here, and then there are this diffuse white bluish kind of emission. So these red filaments are essentially the leftover cool material thrown out of the star during the supernova explosion, while this whitish color is the synchrotron radiation, which I just described, even we see in the radio band. Okay, and we of course see in the optical is the filamentary structure, leftover material, and diffuse emission is the synchrotron radiation. When you go to the ultraviolet radiation, I was mentioning this ultraviolet radiation has shorter wavelength, and because these filaments are pretty cool, very cool here. While, and because the ultraviolet radiation cannot arise from the cool material, so therefore you do not see this filamentary structure. What you see is the synchrotron radiation from the electrons moving in the magnetic field. And now, when you think of the synchrotron radiation, okay, synchrotron radiation we are observing in the radio, in the infrared, in the optical, in the ultraviolet. But the wavelengths are different. So the So the electrons which are emitting synchrotron radiation at different bands have different energies as well. So when we are going to higher and higher photon energies, a shorter wavelength, the energy of the electrons are also becoming higher and higher. In addition, you also see one of the white objects is actually a pulsar, and then you see these background objects which are stars, which are the hot stars which are actually emitting ultraviolet radiation. Now, and then when you look at the X-ray image, it looks very different. First of all, there is this white dot here, that is a neutron star or this pulsar, and then you see a jet-like structure originating from this neutron star, and then these ring kind of structures going from here. All these structures are due to high energy particles which are spewed away by the highly magnetized rotating neutron star. So this X-ray emission essentially tells us the powerhouse of this Crab nebula, which is powered by this Crab pulsar or the neutron star. So you see the diffuse emission, the filamentary structure, the neutron star, how it is powering the nebula. All these things can be inferred only when we have the emission from multi-wavelength radiation or radiation at very different bands. So, but observing or performing multi-wavelength observation in astronomy is difficult. There are several reasons. First of all, a single telescope, when you think, is generally sensitive in one band. Either it is an optical telescope, or maybe an X-ray telescope, or maybe an infrared telescope. You can't have one telescope to observe all the radiation, because that depends on the technology. We are able to detect one radiation in one band. For example, our eye is sensitive to the visible radiation only. Okay. And then this means we need different telescopes, but different telescopes located at different geographical locations, and if you are using that, then arranging observations becomes extremely difficult, because the same object may not be visible by all the telescopes across the globe. Okay. Another problem is that radiations of all wavelengths do not reach to Earth's surface. For example, this figure shows you the different radiations of different wavelengths and where they reach above Earth's surface. Of course, the visible radiation or the optical radiation reaches to the Earth's surface. That is why we have ground-based telescopes, and we ourselves can see the stars. But then you go to ultraviolet radiation, X-ray radiation, gamma ray radiation. Ultraviolet radiation only reaches to about 200 kilometers at an altitude of 200 kilometers. So if you want to observe ultraviolet radiation, then we have to send our telescope and detectors at least at that height. at several hundred kilometers above our Earth's surface. Similarly, X-rays, gamma rays, if you observe, we need space-based experiments. So high energy radiation such as X-rays, gamma rays, and ultraviolet, of course, do not reach to Earth's surface. Therefore, the astronomers need to make special telescope and detectors and place them above Earth's atmosphere. These telescopes and detectors have to work right at the first time. We actually cannot go there and fix it, unlike the ground-based telescopes. So therefore, space-based astronomy experiments are very, very challenging and very, very expensive. Okay, and therefore there are not many of them, in fact. So given that we need multi-wavelength observations, very challenging and expensive space experiments, so then only we get the astrophysics, we can derive the astrophysics astronomy. The construction and operation of a large space observatory, something like Astrosat or Hubble Space Telescope or NASA's Chandra telescopes or ESA's X7 Newton telescope. So the construction and operation of these telescopes, that leads to scientific advancement. This is like the marvel of modern science and technology and brilliance and creativity. So this is very, very challenging. And the effective operation of such facilities, such space-based telescopes, leads to major scientific advancement. Okay, this is very complex process, and it is only possible with the involvement of large number of people, technicians, engineers, and scientists, of course. So it also gives an opportunity to everyone in a way. So this challenge was taken by India, and in particular Indian Space Research Organization and several research institutes in India, and a satellite called Astrosat, which was built, most importantly, this particular satellite has 4 different co-aligned instruments and one more instrument, which is all-sky monitor. These instruments are sensitive in different bands. For example, the ultraviolet imaging telescope here, this is a twin telescope. One of them is sensitive in the far ultraviolet band. And when we say far ultraviolet band, it's about 1200 to 2000 angstrom. The other one is sensitive in the near UV as well as in the visible band, below 2000 angstrom, 2000 to 3000 angstrom, and something like 5000 angstrom in the visible band. So this UVIT telescope here gives an opportunity to observe the universe in the ultraviolet band, in the near ultraviolet band, as well as in the visible band. Then we have another telescope called the soft X-ray telescope, which is sensitive in the soft X-rays, 0.3 kV to 7 kV or so. It can image in soft X-rays, it can take the spectrum in the soft X-rays, as well as it can also measure how the X-ray radiation is actually, how the amount of X-ray radiation is actually varying as a function of time. Then we have another instrument called large area X-ray proportional counters. There are actually 3 such units we call LEXPC 1, 2, and 3. These are sensitive in the hard X-ray band, starting from 3 kilo electron volt to all the way to 80 kilo electron volt. This instrument has a large collecting area. It also has a very good timing resolution of 10 microseconds. What it means is that if a source is varying very, very rapidly, so then this particular instrument can actually see how the X-ray flux is actually varying very rapidly. And that gives a very important astrophysical information. We also have this cadmium zinc telluride imager. This is another hard X-ray instrument, but it can, unlike the soft X-ray, unlike the large area X-ray proportional counter, it can image the hard X-rays. Okay. It can also do timing studies. It can take spectrum. And it can also measure the polarization. Which I did not introduce the polarization, but in the electromagnetic wave, as I mentioned, it is the oscillations of electric and magnetic field. The polarization tells us the direction of the electric field. And it can actually monitor some of the transient sources like the gamma ray burst. As I was mentioning, this Astrosat is an effort of a large number of people from a large number of institutes in India, as well as 2 institutes abroad, the University of Leicester in UK and the Canadian Space Agency. Astrosat was launched in September 28, 2015 and operating successfully even as of today. It's moving in a circular orbit which has an altitude of 650 kilometers and 6-degree inclination with respect to Earth's equator. These are the bands, the electromagnetic bands which are covered by the Astrosat in different instruments. The ultraviolet imaging telescope, as I mentioned, it covers the visible and ultraviolet bands. The SXD, soft X-ray telescope, it covers the soft X-ray band. And X-Space and CJTI cover the hard X-ray band. So all of these instruments kind of covered from 4 electron volt to 100 kiloelectron volt are equivalently 0.125 angstrom to 3000 angstrom or so. This is a wide band, and that is why we call Astrosat as a wide band mission or multi-wavelength space mission. So when you have such a mission, how do you do science? How do scientists do science? How do scientists plan their science? So generally, scientists know, okay, there are several problems. We do not understand the physics of some of those objects. For example, I may not know that, okay, how the neutron star is producing some kind of radiation, how black holes are producing radiation, etc. So scientists generally have problem in their mind, and they think about how to solve such problem. What kind of observations, what kind of telescopes, what kind of wavelength band, etc. are required to address that problem. And they formulate that problem and they simulate that problem and see with this kind of problem can be solved with this particular satellite, etc. And prepare a proposal and then submit to a mission like Astrosat. So this way, the space missions or the space observatories are proposal-driven observations because their operation is decided by the scientific proposals submitted by the scientists all over the world. And those proposals are reviewed, and some of them are actually selected for observations, and the satellite performs observation, and this provides the data, scientific data. That data is given back to the observers or the scientists. They actually study that data, analyze, use sophisticated techniques and computer tools, simulations, modeling, etc. And they finally study or try to investigate the nature of the source or the physics of the source. And that is how the scientific advancement happens, particularly in the case of astronomy, astrophysics. So Astrosat, as I mentioned, it's a multi-wavelength satellite. So what kind of thing we can do? So of course, many of the objects actually emit radiation in different bands. But some of these objects are not variable. In such cases, you can observe today in one band, tomorrow in another band, day after tomorrow in another band, and you can combine and do the science. And that is fine. But this availability of this multi-wavelength capability in one satellite, that is uniquely useful for objects which are variable in different bands. And some of these sources are high energy astrophysics sources, meaning that they emit high energy radiation. And what are these sources? These are active galactic nuclei, which I will talk a little more in more detail. These are the nuclei of some of the galaxies, and these nuclei are very, very bright. They are in some sense activity. We'll talk more about that. Then there are different types of this active galactic nuclei. I'll only talk about a few of them. Then we have binary systems, binary stellar system, where one of the component is a compact object like a black hole or a neutron star, and another one is a normal star. So such objects can also give rise to high energy radiation, and they are highly variable as well. So some of these objects are very, very useful for multi-wavelength astrophysics, and we will look into some of these things. The active galactic nuclei. So as I was mentioning, these are the nuclei of some of the galaxies which are in some sense very active. And this activity, how do we say that this is an active galactic nuclei? Because if you look at the center, the light amount of light output from the center is huge compared to the entire galaxy. Imagine a galaxy like our own has something like 10 to the power 11 stars. Okay, and when we have a light from the center only, from the nucleus only, which dominates the light from 10 to the power 11 stars or 100 billion stars, then there is some kind of an activity. And then we call such objects as active galactic nuclei. And this activity, whatever activity is happening at the center, is not only inferred as the huge radiation power from the nucleus. In some other cases, the nuclei can also launch relativistic jets which are moving with speeds close to the speed of light. Okay, for example, this is a jet in another galaxy called M87. Again, it is an active galaxy. This jet is seen in the X-rays. The same jet is seen in the radio, same jet is seen in the optical radiation. So these are highly energetic events, and these are high energy astrophysics sources. And what are the observed properties? So they have large luminosity and something like these numbers. So what do these numbers mean? So you know the sun, our sun has a luminosity of about 10 to the power 33 ergs per second. And these objects at the nucleus itself are emitting luminosity or radiation power which is comparable to more than billion suns. More than 10 to the power 9 suns that kind of power is emitted from the center only, and that is the huge luminosity. And this luminosity, because they are only from the point-like sources, this huge luminosity is arising from very compact region. In fact, that size is something like comparable to the solar system, or even more compact than the solar system. These objects emit over multi-wavelength, over broad bands. So these are the main properties. I would not go into in too much detail. So what do we know? What do we know about these objects? First of all, high luminosity tells us that the mass of the object should be very large. Why is it so? Because when we have high luminosity, there is a large number of photons being emitted, and these photons interact with the matter, with the surrounding matter, in that particular object. And they impart their momentum, and they push the matter outside. This we call radiation pressure. So if you have large luminosity, that radiation pressure is more, and therefore the outward force is more. So that large luminosity will throw out the material. Okay, so because we are seeing these objects, so that means the objects are stable, otherwise they would not exist if the material has been thrown out. So unless there is a huge mass sitting there, then the gravitational inward pull, that balances the outward radiation force. And that's how large luminosity actually tells us that the masses should be high. And this argument, when just I described, is called the Eddington limit. Okay, so we have a large mass, so given the luminosity of something like, as I mentioned, 10 to the power 9 times the sun's luminosity or so that luminosity, if you substitute here and use this Eddington limit argument, then what we infer is that masses must be at least a billion solar mass. The central nucleus, which is active, that should have a mass more than about 1 billion solar mass, 1 billion to 10 billion solar mass of that range. Okay, and the other thing is that radiation is coming from very compact region. I showed this is from a point-like region, but one can also use the variability argument, because these objects are highly variable. They vary quite a bit, quite a lot in few hundred seconds time scale. So then one can infer that size, which would be smaller than the speed of light, time multiplied by the variability time scale. Okay, that we call the light time argument, and that gives us very small size. For example, 200 seconds, or a few hundred seconds, you multiply with 200 light seconds. And you compare that size with the size of the solar system. For example, from the sun, the light takes something like 8 minutes or so to reach Earth. So 8 light minutes, that is actually much larger than 200 light seconds. So the sizes are actually much smaller in AGN, even compared to the solar size of the solar system. So the huge mass is sitting in a tiny region. Huge mass, something like million to billion times the mass of the sun is sitting in a region which is smaller than the size of the solar system. You can imagine this, how absurd it feels. So in physics, we do not know anything else than black holes, which can have these properties, huge mass, and which are very compact. And because the masses are something like million to billion, we call them as a supermassive black hole. So the supermassive black hole, then what we infer is it is the supermassive black hole which is accreting material towards it. And when the material is coming closer to the black hole, because gravity is attractive force, there is a release of energy. That energy is being converted into the heat and radiation, which we are observing through our telescopes. So that is the basic physics, basic working principle model for the active electric nuclei. We can infer from very, very basic level of physics. Okay, so what we think from previous studies is that there is a supermassive black hole at the centers of galaxies. This supermassive black hole is accreting material, and the material which is being accreted forms a disk which we call accretion disk. Okay, and this disk is formed because of certain physical principles. You may have heard about angular momentum, and because of the angular momentum, these things cannot fall directly radially onto the black hole, but they have to go round and round and round and round around the black hole, and that leads to the formation of an accretion disk. We also need something like a very, very compact hot region. We call it corona, and the temperature is very high. Energy of these electrons here is very high, which that is why they emit in X-rays, and there can be relativistic jets arising from the very, very central region. Okay, and when we want to study, study these systems, we want to probe using our multi-wavelength observations what is happening near the supermassive black hole. Because in laboratory, this kind of thing is not available. It is only in astrophysics where we can probe such extreme regions near the supermassive black hole, because there is a lot of complicated physics is going on. And that's the purpose of some of these observations. So one basic thing we can infer, or we can study using our own Astrosat, which is the accretion disk. As I mentioned here, Here, this accretion disk here, we can very simply study. For example, there are models, there are physics-based models for accretion disk. And what these models tell us? These models essentially tell us that the accretion disk is geometrically thin. Okay. And the temperature of the accretion disk actually varies as a function, as a distance from the center where the black hole is located. So in the innermost region, the temperature is highest. And when we go outward, the temperature actually decreases according to this law, according to radius to the power minus 3/4. So the temperature here in the innermost regions is such that the radiation peaks in the extreme ultraviolet region, which is kind of a few hundred angstrom region, or close to 1,000 angstrom region. And outside, the temperature decreases and then it starts emitting far ultraviolet, near ultraviolet, even infrared. Okay, so if you can now divide this accretion disk in terms of various rings, and then say, okay, the innermost rings emits the extreme ultraviolet, and the rings in the middle regions, they emit in the optical, and in the outer regions actually emit in the infrared. And then you can sum all the radiations which look like black body radiation from different rings, because they are at those temperatures. And then you have the final spectrum of this accretion disk, which comes in the ultraviolet band, optical band, even in extreme ultraviolet band. Because Astrosat is sensitive in the ultraviolet band, we can actually look into the spectrum. For example, the spectrum of some of these objects, and here are these observations. When I say spectrum, it is the amount of radiation plotted as a function of wavelength or frequency or energy. Here Here it is plotted as a function of wavelength. So then the intensity or the amount of radiation which is plotted as a function of wavelength, that is the spectrum. And in the theoretical models give us this kind of spectrum over from the infrared to all the way to extreme ultraviolet. And we have in the ultraviolet spectrum, and we can then observe with Astrosat, get this spectrum, measure the shape of the spectrum, and compare with the models. And then see whether the models are actually correct or not. And this is what we have done in using Astrosat. And what we find in some of these active galactic nuclei, the accretion disks do not extend to very close to the black hole. They are actually truncated at some intermediate radii. This is another kind of observations, because the AGNs are multi-wavelength emitters. They have optical radiation, ultraviolet radiation, X-ray radiation, even gamma ray radiation. And they are highly variable. They are kind of restless creatures. Okay, so the ultraviolet is variable, X-rays are also variable. So here one can study how, that is the advantage of having Astrosat, because it can observe simultaneously in the ultraviolet and X-rays, and we can probe how the radiation in the ultraviolet is varying and how X-ray radiations are varying. Is there any connection between these two? We can use that kind of observations to probe the central engines of AGNs. And we did that we have done that using Astrosat. This is a 4-day long observations of one of the active galaxy called NGC 4051. It has a black hole of mass 10 to the power 6 times the mass of the sun. Okay. These are the images. This is the X-ray image of 10. Actually, it is a point light. This structure is just because of the telescope. This is the far ultraviolet image at about 1700 angstrom. This is the near ultraviolet image at about 2000 angstrom. So here you see this is the AGN. This is the AGN, and this is the galaxy of this associated with this AGN. Okay. So when we look at how the UV and X-ray varies, these are the so-called light curve. Light curve tells us the amount of radiation as a function of time, or the intensity as a function of time. And this is how the X-rays is actually varying. This is how the far ultraviolet and near ultraviolet are varying. Now we can analyze these light curves or the time series data and see whether there is any connection between these light curves. And we do find with detailed analysis that the ultraviolet emission is delayed compared to the X-ray radiation. Okay, and then we can use this information and prove the physics of the central agent, the accretion disk and the hot corona, which we have done using Astrosat. This is what happens to tell you a little more detail. So this, when we say corona, this is nothing but hot energetic electrons with the electrons have energies of order of 100 kilo electron volt or so. Then this accretion disk is emitting optical ultraviolet radiation. And this optical ultraviolet photons are actually traveling here. Then they are getting converted into X-rays due to inverse Compton scattering. And these X-rays are illuminating back onto the disk. And then they are getting reprocessed by the disk and are being observed. So there's a lot of complicated stuff going on, and this complicated physics we can probe with the variability observations in different bands. So last thing I would like to tell is about black hole X-ray binaries. As I was mentioning, these are binary stellar system. One of the compact object in this case is a black hole. In this case, it's a stellar mass black hole, meaning the mass of the black hole here is of the order of 10 solar mass or so. And this is in the binary system with a normal star like our sun. Okay, and this black hole, this material from this normal star is essentially being accreted by this black hole due to its strong gravity. And that process again forms an accretion disk as well as relativistic jets, etc. And here also you have ample amount of X-ray radiation, even ultraviolet radiation, and then one can study the physics near the black holes. And this Astrosat has done quite a lot of these studies. And what are the observational characteristics? Some of these objects are pretty much quiescent, pretty much very, very silent, for a long time. But then sometimes they go in a huge outburst when their X-ray flux increases by factors of several hundred. Like this, these changes seen here, those are the outbursts. And when they go into the outburst, their accretion disk and the hot corona and the relativistic disk change, and they go into different kind of states, which we have names for these things, which I do not go. So, but the importance is that whenever there is a huge outburst, catching those objects and observing them and during the outburst, and then looking at how the X-ray radiation, how the UV radiation, etc. is varying, how the spectrum is changing over time, and then probing how the engine, the black hole accretion disk hot corona system is changing as a function of time, how the black hole strong gravity is playing a role as these systems evolve. All these things is possible to study with Astrosat, and that has been done quite a lot. And that is where, because these objects are also very, very rapidly variable on time scales of milliseconds or so. And that kind of variability study is possible with this Astrosat instrument, LAC-PC, Large Area X-ray Proportional Counters. One of the things we did here, and this is the one where we use all Astrosat instruments to derive its a multi-wavelength spectral energy distribution, the intensity of the radiation at different wavelengths in the ultraviolet, in the soft X-rays, in the hard X-rays, etc. And then we try to model these things with accretion disk hot corona models and infer its geometry. And when we infer, what we think is that there is a black hole, and this black hole accretion material forms an accretion disk like this, and there are this hot corona like this in the innermost regions. And this is in one of the state which we call the soft state, where the accretion disk emission actually dominates. There is another state of the same object where our Astrosat observations tell us that the region very close to the black holes have actually changed. It's a physical state, and we can actually infer those things with our observations. I will not go into the details because these are more technical stuff. So to summarize, India has successfully built and operating a multi-wavelength astronomy satellite, and this multi-wavelength capability of Astrosat is being used for multi-wavelength spectroscopy and variability studies of active galaxies, X-ray binaries, etc. You can find more details about the Astrosat mission and various details about it, even observing opportunities, project opportunities, etc. With the Astrosat Science Support Cell website, which is at IUCA, where I work. You can visit this link and you can find more information. Thanks, of course, to Indian Space Research Organization, the instrument teams, the payload teams, the operation teams, and of course the Astrosat Science Support Cell. So here I'll stop. Thank you for listening.
Can I? Okay. So thanks, Gulab, first of all, for coming here and for the fantastic talk that you gave.
Thank you.
So I have a question for you. So we have this Hubble Space Telescope, with also has multiple bands in which we can observe the universe. And now India has Astrosat, which has a similar capability, maybe in different bands. So is there any synergy between these two telescopes, and how can one take advantage of this synergy?
Yes. So first of all, the advantage of Astrosat is having UV as well as X-ray instruments on the same platform. So with the Astrosat, one can perform simultaneous ultraviolet, X-ray, soft X-ray, hard X-ray observations, and perform multi-wavelength observations. The imaging, of course, the imaging quality of HST, particularly in the optical band, etc., is very good. We all know, we have looked at the images. It also has very good spectroscopic capability. But as far as the for ultraviolet band, which is going down to 1200 or so, and we want to study the nearby universe, in the high redshift universe, of course, even if you are looking at the optical, etc., you will get the emitted radiation in the ultraviolet. When we want to study the nearby universe, the associated UVIT also has a fantastic imaging resolution, and that is supported by X-ray, etc. So that part, particularly to study this far ultraviolet and its connection to X-ray, that is where the associate plays an important role. Otherwise, if you really look into the comparisons, the Astrosat UVIT has designed in such a way that it has a very, very low background. Okay, and that can detect very faint sources if you integrate for a longer time. And that is the reason why a distant galaxy was the Lyman, the emitter galaxy. That was actually discovered with Astrosat, and which published into Nature. And that was difficult in getting in HST. It is even having a small telescope with a very careful design actually discovered, and that result was published by Nature by Kanakatel, in fact.
Thanks a lot. Thank you.
So are there any more questions?
Hello sir, thank you for your fruitful knowledge about multi-radiation and their rays. So you explained us a topic about AGN, active galactic nuclei. So you told that there is high luminosity, large mass and rapid variability. Can you give some idea about rapid variability?
Yes. So when I say rapid variability, what I mean to say that we use our telescopes and look at the intensity. For example, the X-ray intensity or flux, or you can just say how many X-ray photons are coming every second. And then you count that number and how that number is changing as a function of time. And in the case of AGNs, what we see is that the intensity or that intensity of X-rays is changing by about a factor of 2 or 3 in a few hundred seconds. And that is what I'm calling in the case of AGNs a rapid variability, given the huge luminosity, and that are variable in as short as 100 seconds or few hundred seconds time scale. That is the rapid variability we are calling.
And sir, how do we observe a black hole, using optical radiation or X-ray or UV?
So the rapid variability is generally observed at high energy radiation in the X-rays as well as in the gamma rays. When you look at the variability in the optical variability is much slower, which also tells us that using X-rays we can actually probe the regions very close to the black hole, because if the radiation is arising from the compact region, that will be more rapidly variable. While the radiation is arising from much bigger region, the radiation will be less variable. So that is why we use X-rays to study the regions very close to the black hole.
Thank you, sir.
So if there are no more questions, let's thank Professor Dewangan for this fascinating talk.
Thank you.
The universe is truly a fascinating and vast space. So now we'll all break for tea and snacks, and we all meet here in around 20 minutes. So please feel free to chat and discuss and interact with the speakers with whatever you have learned so far. So the snacks counter are set up right outside this auditorium. You can exit the auditorium through the right door. And we'll meet back here by 11:45. I would request the students to please remain seated and maintain the decorum of the hall. So, welcome back everyone. I hope you guys enjoyed the break, and let's dive into the next exciting topic that we have. So our next speaker for the day is Professor Shashi Ganesh from PRL Ahmedabad, who will talk about how we observe the universe from a unique vantage point on Earth. Dr. Shashi Ganesh is a professor in the Astronomy and Astrophysics Division of the Physical Research Laboratory. He has interest in observational astronomy and in the development of instruments for telescopes operated by PRL at the Mount Abu Observatory. His research interests span solar system objects to the Milky Way as a galaxy. He has guided several PhD students on various topics in astronomy. The talk is titled Observing the Universe from Spaceship Earth. This session will show us how our planet is a powerful observation platform for exploring the cosmos. Please welcome Professor Ganesh with a big round of applause.
Is it okay? Yeah. Yeah. And the slides move also, right?
It has moved. This is the laser button.
Yes.
This is the laser and these are the...
These are the... Okay. Okay. So, very good morning to all of you. And I'm really happy to be here, quite excited to see such a lot of budding scientists, and I hope that we'll have some interesting discussions, okay? So I have a lot of slides, okay? So there are two ways that this talk can go. One is that I just show you all those slides, and then we can have a discussion maybe of a few minutes at the end. The other is that I can, display the slides one by one, and maybe we should actually have a more discussion kind of thing. So if there are any questions in between, please feel free to interrupt and ask questions. And I will also start with a question. I have written the title, Observing the Universe from Spaceship Earth. So how many of you will agree that we are on a spaceship? Okay. Okay. A few hands. So what is a spaceship? Somebody would like to say? What do you understand by a spaceship? Anybody? I mean, you have seen a lot of photos, right? Yeah, the hand at the back. Yeah, I want them to answer. I can't. Yeah.
Sir, spaceship is a type of machine in which the humans can move in the universe for a while with any resources like to move a spacecraft.
Mm-hmm.
So Earth is one type of spaceship, as you say. We are living in the Earth, and the Earth is moving, and our solar system whole is orbiting the galaxy.
Okay, excellent. So yeah, that's the thing. So a spaceship, yeah, very nice. Good. So everybody is paying attention, very good. So as he said, the Earth is a spacecraft because it is giving us the life support system that we require, which is always there on any spaceship that you see, right? Whatever photos that you take. So what I'm going to show you is that on Earth, it's possible to do a lot of things by looking up at the night sky. In fact, you don't need anything much more than just your eyes to go out and look at the night sky, okay? So that's something which we should all really be happy about, because India, especially the rural places, are still having the benefit of dark skies, okay? It's slowly going away with people adding a lot of light pollution, but hopefully, yeah. we will see how things have changed in other countries, but here we still have the possibility. Now, our story of understanding of the universe is a story of the evolution of our telescope technology over the last 4 centuries. You know, right, that the telescopes were discovered invented around 4 centuries ago. And yeah. Anybody know who actually invented the telescope? No? Yeah.
Sir, Galileo Galilei had invented telescope.
Galileo Galilei, okay. Okay.
I think it was the Hans Lippershey.
Hans Lippershey, okay. So we have 2 different answers. Hans Lippershey was actually a Dutch optician, and he was the guy who actually made this instrument. Galileo was the first to actually look at the night sky using a telescope. He was not the first to make it, but he was the first to look at the night sky using the telescopes. And this telescope, in fact, these are replicas which are still available, and these are sufficiently powerful to show you a lot of interesting things which you can in fact build with your own hands. Okay, you just take a specs lens, the reading glass type which people use. Once you reach a certain age, वो दूर का चीज़ दिखता नहीं है, तो पढ़ने के लिए ये यूज़ करना पड़ता है ना, स्पेक्स यूज़ करना है. तो वो स्पेक्स आप यूज़ करके उसको you put it in a tube at one end, and you put a small focal length eyepiece at the other end. Okay, तो उससे एक बहुत अच्छा सा टेलीस्कोप बन जाता है in about 1,000 rupees के अंदर में. With that kind of telescope, it's easily possible to see the rings of Saturn, craters on the moon, and even Jupiter's satellites. Okay, so this is something which you people can easily do in your school. Okay, something which I did when I was a student. Okay, I also built a microscope, but that's a different story. So Galileo was the first to look at the night sky, and he resolved the stars of the Milky Way using his telescope. Till then, people thought that, okay, the Milky Way is actually a band of milk or whatever. Okay, they did not realize that it was actually stars, individual stars in large numbers. Now, next, and then he was the first to actually document. See, it's not enough to do the work, it's also important to document what you are doing. Okay, document what you have seen and show that to the world. Okay, that is what is important. So he was the one who did this, and about 4 centuries ago, he wrote these very interesting documents and listed them out. So the kind of telescope which Galileo built was a refractor. Okay, it made use of lenses. Newton came along and he made another telescope of this kind using mirrors. Okay, so the advantage of mirrors is that you can support them from the back. Okay, which means that you can make them much bigger than you can make a lens-based thing. Why do you want to make bigger telescopes? Somebody wants to answer that question? What does a telescope do? So a telescope is usually meant for collecting light. Okay, the bigger the telescope, the collecting area, more deeper you will be able to see more fainter objects. Okay, so that is the reason that we go for building bigger and bigger telescopes. Okay, the biggest telescope on Earth right now is with a mirror about 8 meters across. That's about the size of the stage. But there are telescopes which are going to be 25, 30, 40 meters across, about the size of this auditorium. Okay, so the mirror is of that size. You can imagine the size of the building which will be required to house that. Okay, so Newton was the one to make this kind of a telescope, which had a reflecting mirror here, and then light comes in from this side, gets reflected into a smaller mirror at this point, and comes out to the eyepiece. Okay, so you look through the side of the telescope. So this was Newton, and of course he also did a lot of writing up and then published all his results. He was also the first to actually split the sunlight into the spectrum. You all have seen the rainbow, right? Rainbow dekha hai na? So Newton was the first to explain what is actually happening over there. And he used a glass prism and sunlight coming in from the side and showed that the light of the sun actually constituted of 6 to 8 different colors, okay, the Vibgyor, which people say. And in fact, the next person that I would like to highlight is William Herschel. And he was actually a musician by profession, but he was an amateur astronomer by practice. And he was the first to actually look at the night sky using his telescopes, which he built himself. And he was the one who did the counting of the stars of the Milky Way and made the first map of the Milky Way. Okay? So until then, people were just looking at different objects, and people did not really know what is happening. People were still thinking that the sun is at the center of the universe. In fact, even Herschel said that the sun is at the center here. Can you see this dot? And then he found that it is actually going in 2 different directions. Okay, we'll come to it in a moment. The other thing which he is remembered for is that he discovered infrared radiation. Okay, so he did the same experiment that Newton did, and he actually kept this kind of thermometers. Okay, so he kept thermometers on the side, and then he split the light from the sun, and he found that when the thermometer which was sitting on the red side was also still having some amount of light coming. I mean, there's some energy coming there compared to the thermometer on the side of the other side. So that was what he called infrared radiation. And this was a very important breakthrough. That is when people realized that electromagnetic waves can be of different wavelengths which the human eye cannot see. So that is another point which is a characteristic of spaceship Earth, that you are able to. So anyway, this is the spectrum which I wanted to show you in more detail. I think we'll skip this. This slide you have already seen. We'll come back if needed. But this is the slide which I want to show you. So Newton showed these, that the visible light is actually built up into multiple colors. And Herschel showed that there is infrared radiation coming even beyond this. Okay, so in the excuse me, beyond about 800 nanometer. And if you look at the Earth's atmosphere, it's a perfect blanket. No spaceship can actually reproduce this. That is why when people go on the moon, for example, the astronauts who walked on the moon, they had to have very well-equipped spacesuits, okay, to step out into the sunlight. Okay, so because if you are exposed to this kind of X-rays and gamma rays, then your molecules will break down almost instantaneously. So you need to be protected from that. So that's another reason why spaceship Earth is to be thanked, that we are protected from all these harmful radiations. Now, you also have infrared bands which need to be observed from space, but there are some from the ground. Radio waves we can observe from the Earth, but again, gamma rays, X-rays, as the previous speaker, Professor Dewangan, was telling, it's completely blocked from the Earth's atmosphere, by the Earth's atmosphere, so you need to go to space. But let's see what we can do. How many of you have seen the Milky Way? 1, 2, 3, 4, okay, 5, nice, not bad. So all of you are from Ahmedabad, you have seen it, or, okay, from Ahmedabad or from some, kahan pe dekha? Huh? Internet, okay. No, directly with your eyes, have you seen? So jo bhi Ahmedabad se hai, it's very unlikely that you would have seen this spectacle. But if you go to Mount Abu or any dark site, this is the kind of band that you can see, okay. It looks, जैसे अहमदाबाद में फॉर एग्जांपल कभी कभी बादल का पैच आता है ना, तो बादल जैसे दिख रहा है ऐसे माउंट आबू में क्लियर नाइट में ऐसे दिखता है. Okay, so you can see hundreds of this kind of stars. This is just a small part of the sky, and this is a normal camera. It's not anything special. So ये camera को you just put it on a tripod, take a 30-second exposure, you will see this kind of stars. Okay, not just the stars, but then the gap in between. You see, that's something which puzzled a lot of people in the past. Okay, so almost for 100 years. People were thinking, ये gap यहाँ पर, is it really that there are no stars there? So people sometimes call them holes in the heavens. Okay, कि वहाँ पे कुछ है नहीं, stars नहीं है, there is a blank gap. But when we started looking at these regions in infrared domain, infrared का benefit क्या है? It penetrates the dust. Okay, so it's able to go for, you're able to see more objects. So ये तब पता चला कि यहाँ पर it is not just blank space, but actually there is material between the stars, and that material between the stars is obstructing the view of the night sky in these directions. Now let us see what it looks like if you were to use infrared space observatory to look at this part of the sky. So I am going to show you a very small patch here. Okay, this is an image which actually I made about 2 decades ago, using data from the infrared space observatory. Okay, so this was the first major space observatory which looked at the night sky and took images of selected areas in the galactic plane. And this part, this circle here, is the center of the galaxy. People thought that it would be too bright to see. That is why it was not observed using this spacecraft. But the next spacecraft, about 10 years later, is the Spitzer Space Observatory, and that looked at the same area of the sky, and you see the number of stars here. Okay, it's impressive, right? So when you look at this one, you're seeing something like maybe 15 to 20,000 stars. Okay, if you actually sit and count these dots here, you may see around 15 to 20,000. But the moment you go to infrared, there are about 1 lakh stars in a small part of the sky here. And here, can you count? Right? So it's not something that you can sit and do by hand now. People have done that in the past. When we did not have computers, we did not have mobiles, people were very interested to know what is the universe. They actually spent time looking through the telescope, with their eyes, and counted the number of stars. Okay? So that was the simple method of actually understanding how our galaxy works. So exactly the same thing we are doing now, but now we are using computers. Okay? So we are counting the number of stars in each of these directions. This extremely bright patch here is the center of our galaxy. Okay? And again, these dark clouds here are again also material from between us and the stars in that direction. Okay? So this is the galactic plane. Now, I can spend an hour on this, right? We can keep discussing this kind of images, and but then that will not help us. Let's go ahead. What does it look like when you start looking at the entire spectrum? Okay, you heard from Professor Dewangan that you need to look at the night sky in all the bands that are possible. Now, the Milky Way. You know, I showed you the Mount Abu photograph. I'll just recall it one moment. Yeah, this one, okay? So this image, if you look at the entire night sky, entire galactic plane, then that is this one, okay? This patch here. If you were to use an infrared telescope, this is the kind of image you would get, okay? So you're still seeing the stars there. But as you go to longer and longer bands, you start seeing the molecular emissions. Okay, so the molecules and the dust, they start emitting at longer wavelengths. In the X-rays and in the gamma rays, you start seeing higher energy radiation. So these are energetic material like hot electrons and plasma. And X-ray objects, X-ray binaries and those kind of objects start dominating. So you see that the Milky Way looks extremely different as you cross the spectrum. Coming back to spaceship Earth, I'll just quickly run through a few slides just to give you a sense of scale. Okay. Now, I want you all to imagine that the sun has been squeezed to the size of a tennis ball. Okay, I'm going to keep the tennis ball here. And then let's see where the planets are. How many planets are there? Yes?
8, sometimes 9.
8, sometimes 9. Okay, so, all right. Why 8, sometimes 9? Yeah, come on. Yeah, so 8 means that Pluto is not included, 9 means Pluto is included, right?
Because the 1 is left.
Yeah, 1 has been left out. So, some in 2005 or 7, I think, the astronomers around the world decided that Pluto was too atypical to be a planet. That is why we say sometimes 8, sometimes 9. There are hundreds of other objects like Pluto, okay? So that is why we say that it's 8. But that is when you talk about our solar system. So it's 8 planets we know in our solar system. But suppose we say in our galaxy, then how many? Anybody wants to guess? So there are about 5,000 known exoplanets, okay? Target kind of. So now let's come back to the solar system. I said we are going to keep a tennis ball at 0. Where will be Mercury and what will be the size? Mercury will be a mustard. राई होता है ना, खाने में बनाते हैं, right? वो राई का दाना होता है at about 3 meters. Okay, so that is the kind of scale in the solar system. Now, what is next? Venus. Venus is a slightly bigger mustard seed, okay, at about 5 meters. So the sun is here where the bottle is. Mercury is somewhere there, and Venus will be somewhere where you people are sitting. Where is the Earth? It's a 7 meters, okay. Now, Earth to Moon is how much? Anybody wants to guess? Two centimeters from the Earth. Okay, it's next door, practically. So nothing special. It's just that it's co-orbiting with the Earth. Mars is the 4th mustard seed at about 11 meters. Jupiter is at 37 meters. Okay, so there's a big gap after Mars, and you have P. That means so watana hota hai, matar. So aloo matar. So वो वाला, that is at 37 meters. उसके बाद आता है Saturn, and that is at 69 meters. So these are all well beyond this building, okay? And then you can have Uranus, it's at 140 meters, and then Neptune at 200 meters. So still you are within the campus, okay, within the IIT Gandhinagar campus. But even with all that much empty space, that means what? That the solar system is essentially an empty area. Okay, it's the best kind of vacuum that we can achieve on Earth. So even with all that empty space, there are times when objects collide with each other. Okay, one such fantastic example is when Jupiter was hit by a chain of 21 comets. Okay, so this happened sometime in 1994, I think before most of you people were born here, I guess, except some of the people in front and me. I happened to be able to see it, in fact, with a small telescope. The telescope I made using mirrors, which I made at SAC actually, and Professor Kiran Kumar's lab. It's a fantastic experience, to make the mirror yourself, and then not just make, but actually use it to see the night sky. So something that's remained with me. So these dots were easily visible. Now you can imagine the size of these scales here. This is Jupiter. Earth, if you were to keep here, would be as small as this patch. Okay, so the comet, when it collided with Jupiter, it left Earth-sized debris, right? So if it were to have hit the Earth, what would happen? Something that I think the dinosaurs know very well, right? So In fact, that's the reason that we say that Jupiter is our protector. Okay, it is avoiding this kind of material coming into the inner regions. Okay, so we mentioned that Pluto is a minor body, it's no longer a major planet. So there are many such objects in the solar system, and we would like to study and understand these. But why? Okay, why is one thing. First, I'll just tell you where we find them. So I mentioned that large gap between Mars and Jupiter. It's made up of a large number of rocky bodies. Okay, these are called the asteroids. Now, the theory is that they are very close to Jupiter, and then because of the presence of Jupiter and Saturn, it did not allow the formation of another big body in the gap between Mars and Jupiter. Okay, so this is the major belt called the asteroid belt. Similarly, you have, as you go outward, you start seeing more material which sometimes comes into the inner regions of the solar system. How many minutes do I have now? It's about 10, 15. Okay. So, so we have this kind of, so this is the asteroid belt in the inner solar system. Jupiter is here, and as we go out, you have the Kuiper belt of objects, which are again small bodies, like the asteroids or like Pluto, in fact, but hundreds of them. Okay, and these are objects which sometimes come towards the inner region of the solar system, and when they come closer to the sun, then they give rise to what are known as comets. We'll see some examples of that. Now, exactly the same thing which I've been telling you, but in logarithmic scale. You understand logarithms? Right? At least some of you would, but some of you will learn about it. So in this is the solar system on a logarithmic scale. So you have the sun and then all the inner planets and the major gas giants. And then you have the location where the first man-made object has just exited the termination shock. That's the effect up to which the sun's effect can happen. And then you have the Oort cloud, which is a spherical shell of material around the solar system. So this is a hypothetical cloud, which is on the basis of observations that people say that there must be a material cloud over there, okay? Because you see comets coming from these kind of distances. So this unit here is with Earth. Okay, so I think I'll skip this slide. It's just basically about the history of how comets have been considered as omens and signs and all that until people really understood what comets are. Comet Halley. Comet Halley is a very interesting comet. It is the only comet which is named for a person who was a theoretician. Okay, all other comets are named after the people who discovered them. Okay, but Halley was the one who predicted that the comet which was seen in sometime back in history is the same comet which is going to come again. And he did not live to see that, but his prediction came true, and that is why Comet Halley is called Comet Halley. Okay, so that's something. Why do we study? Why do we want to study comets? I already mentioned that they are building blocks of the solar system. That is why we want to study them. So they are the leftover material, okay, from the time of formation. तो इसका मतलब ये हुआ कि आप क्या खाए हो उससे ही आप बने हो. तो by looking at what you left behind on your table, can you tell what you are? That's the kind of inference that we are trying to say. Okay, but other reason that we want to understand comets is because each comet is different. Okay, every comet looks different. I'll show you a few photos. I'll skip this. Yeah. Spaceship Earth. Okay, this is a photo taken from the International Space Station, looking across the limb of the Earth. Okay, so this, you see this lower patch here? That's the Earth's atmosphere. Okay. There's one very interesting story about the size of the Earth and the size of the Earth's atmosphere. So, You know, we have to, when you're doing your PhD, you have to do your coursework, okay? So at that time, our instructor told us that the Earth is the size of an apple, then the size of the atmosphere is the skin of the apple, okay? So in the final exam, of course, he asked what is the Earth's atmosphere, what is Earth? So the answer was Earth plus atmosphere equal to apple. Okay, so that's the thing. So here it actually shows you. So you have 6,000 kilometers of the Earth, and then you have a few hundred kilometers of the Earth's atmosphere, and you can see it here. This green line is the oxygen layer at the top of the Earth's atmosphere. So this is a layer where most of the solar radiation is getting blocked. And why is this an important image? Because here you can see a huge number of different objects at different distances. This is the comet, which was called the Christmas comet, discovered in December 2011. In fact, it was discovered just before it came close to the sun. And then after it came back from the other side of the sun, it gave us a very spectacular view. And this is the tail of the comet. This is many degrees long. And in fact, it's visible simply because he took a long exposure photograph from the International Space Station. This, in fact, gave a lot of very interesting comet photos. There are two different tails here, right? Can you see? You see one tail here and one tail here. Is this? This is in the optical band. Oxygen 5577, that's green, and then you have 6300, that is red. So both those bands are visible. Actually, you see them in Hanle very nicely because the sky is really dark. So, okay. So this is a photo of a comet taken by me from our Mount Abu observatory. Okay. So this was a comet which was bright in 1997. Okay, it was discovered by two different people, Thomas Hale, and Alan Hale and Thomas Bopp. Okay, two different people, and that's why it was called Comet Hale-Bopp. And this was taken with a film camera. Okay, we mounted a film camera. Before the digital cameras which you see in your mobiles, we used to use film, where we had to keep it on a stand and take a long exposure. So this we did for 2 minutes. We exposed the image for 2 minutes, and that is why you see these. These are all stars, but they appear like trails, right? That is because of the Earth's rotation. So you're actually seeing how the Earth is rotating, and in fact, even the comet has shown. So here you see again two tails. Okay, so the two tails are coming because of material coming out of the cometary nucleus. The dust is this white yellow patch, and it is also moving out in the same orbital mechanics method as the rest of the comet body. But the lighter ions and neutral material, that gets blown away by the solar wind, which is almost radially outward. Okay, so that's how you have two different tails. Now, different comets show different behavior, as I said. So this is another example where you have the tail. Depends upon how you are viewing the comet. What is the geometry of the orbit, and in what angle you are seeing the comet. Okay, so what else can we do with cometary objects? You can actually study their spectrum. We showed you the rainbow, right? And from that you could tell what is the composition of the stars. We know that stars are mostly made of hydrogen. Does anybody know how long ago it was that we were wondering what they are actually made of? It's just about 100 years that we know that stars are made of hydrogen. Before that, we really did not know that. Okay, so that answer came through doing spectroscopy. So, so that has been done for comets also, and then we have spectra. Okay, spectra of the comet, which shows you on top of the continuum emission, you can see the molecular bands. Okay, so these are coming from different types of molecules. which are in the comet's coma. Okay, we'll get into it in more detail if people are interested. Now, all the comets that we have looked at so far are comets which were belonging to our solar system. But recently, there were two objects which came with the kind of velocities which they cannot allow for solar system bodies. So these are objects which came from other planetary systems, from other stars. Okay, so these entered the solar system, came close to the sun and went away, and there's no way that the sun could catch hold of them, even with all its enormous gravity. So one was an interstellar asteroid, that was 1I, and the second interstellar object is a comet. And in fact, this comet was something spectacular. It did not become as bright as some of those very interesting photos which I showed you, but we were able to take images with our Mount Abu telescope, and we were able to take spectra with our Hanle telescope, which is just 2 meters across. All previous observations of this comet were with telescopes about 8 meters size, but we were able to provide the first set of measurements after perihelion, that means after it had passed the sun. And then we came to the conclusion that it's very similar to the comets of the solar system. That means, what does it mean? That means that the processes which led to the formation of the sun are very similar to that which led to the formation of other stars and other stellar systems. Okay. So I'll just conclude with a few other interesting images. This is another example of a fantastic comet. This is the comet next to the Himalayan Chandra telescope at Hanle. This is at an altitude of 4,500 meters. If you have gone to Ladakh, you will know that you will need to acclimatize once you are there. So at this place, you cannot stay for a very long time, except those who are local people. And here also you see the red sky at the back. Okay, that's again from the oxygen atoms in the Earth's atmosphere. And this is the ion tail and the dust tail. There's spectacular images from these places. One final, I think, example photograph. This one is a large field of view, okay, so 10 by 9 degrees. You know, the Earth, the size of the moon or the sun is about half a degree across in the night sky. This object is 10 by 9 degrees, okay. So there are times when comets can be the biggest object in the solar system. They become bigger than the sun also, okay. It's just that the material is too small, but they can be at times bigger than the sun. Okay, how does that comet look like when you look at it through a big telescope with a small field of view? So this was the full field of the comet. If you blow up the small region here, this is what the comet looks like using a 2.5 meter telescope. These were the first images of that comet from our telescope. The 2.5 meter was installed in 2022, and these were images taken in 23. Okay. I don't know if, okay, I have a few slides. If I have time, I can talk a little bit about our 2 minutes. Okay. So I'll just conclude with, we have been showing you slides and photos about what other people have been doing. I'll just show you some images or some slides about what we have as facilities at PRL. And if sometime, some of you, after you finish your masters, you can come and join us and work with those tools. So we have one very important thing. We have a very dark and blue sky. Okay. We are at the height of about 1,700 meters above sea level. So that means that we are well above most of the polluting atmosphere. Beyond that, we have several telescopes. We have a 50 centimeter telescope here, a 43 centimeter here, 1.2 and 2.5. The 50 is shown here. And on that, the telescope is just one part of the thing. The telescope is only for collecting light. What do you do with it? You have instruments at the end of it. Earlier we used to look through, but now we have sophisticated electronics, which helps us to do a lot of things. Okay, so for example, with this one, we have we have an imager and we have a spectrograph, so you can actually make a spectrum. This also is a 43 centimeter, which is having a imager. This is a telescope which was actually built by ISRO for PRL. It was in fact built by SHAR Center of ISRO. The mirror was built in Bangalore and by IIA, and it was installed at Mount Abu in 1990s. And we have many different instruments at the back of it, and many of these were built by PRL scientists. Some were purchased, but most of them were bought. Most of them were made at PRL for the kind of work that we are interested. And the latest is this 2.5 meter telescope. So this 2.5 meter telescope is something which has just come up, and we are now very busy working with this, with all these 4 instruments, and hopefully you will be able to also make use of some of these. I think I'll just, something to think of. You know, I gave you the size of the solar system, about the size of this campus. Where is the nearest star on that scale? Anybody wants to guess? Kalupur. Too close. Too close. Ahmedabad. Think of Bombay. Bombay, Chennai, yes. That's Alpha Centauri. So it's something quite, I mean, space is enormously vast and empty. Okay? But yeah. And the other 2 are, I think, they are too difficult to. Okay, I'll stop here. Take questions.
So the floor is now open for questions.
Yes.
Sir, what is the meaning of minor bodies?
Minor bodies, okay. See the 8 major planets, so they are called the major bodies, okay? So they are the planets which are moving around the sun. The minor bodies are objects which did not condense enough to become big bodies themselves. So these are the building blocks of the solar system, and these are rocks and ice, okay? And they can be of sizes from, let's say, few stone sizes, maybe few centimeters, to maybe a few kilometers across, okay? So that's the minor bodies.
What is the meaning of comet?
Comet is again the same object. When it comes closer to the sun, then the heat of the sun causes the material to evaporate, okay? Yeah, I think.
So it's better to ask a single question per person, since we have to accommodate so many people. Yeah.
Sir, what is the age of comet?
Age of comets. Okay, nice. So people have, okay, I will answer it in a slightly different manner. People have measured the age of the meteorites which people have collected on Earth. And meteorites are of the same kind of material of which the comets are made. And that comes to something like 4, 5, 6, 7 million years. Okay, it's a nice number, 4, 5, 6, 7. So that's the kind of age of these objects. So that's the age of the sun, in fact. It's about 5 billion years. Yeah.
And what is the diameter of the black hole?
Black hole. Now it depends. That's not something very easy to answer, but it's like an entire galaxy sitting inside this campus. Okay, so it's a few hundred meters size. Yeah.
Okay, thank you.
So which is more dangerous, comet or asteroids?
Which is more dangerous, comets or asteroids? Okay. How do I answer that? Okay. So actually comets and asteroids, what's the difference is that comets happen to show an extended material, okay? So these are objects which have a lot of ice and gas in that, okay? Whereas asteroids are more rocky. And then the thing with comets is that they are much bigger. So if they were to hit the Earth, then the consequences could be quite disastrous. But they are not as numerous as the asteroids. In fact, every night there are at least a few asteroids the size of like a car or a bus, which are coming very close to the Earth. In fact, some of them even hit the Earth. Okay? Many of them burn up in the Earth's atmosphere, but most of them, so answer is a bit qualitative. Both are equally dangerous. It can destroy a city or it could destroy life on Earth as we know it. Okay?
Which kind of glass is used in Galileo's first telescope?
Which kind of lens? So this reading glass hota hai na? So let's say you take plus 0.5 power.
Okay.
Positive power plus 0.5 or 1. If you take 0.5, that means 1 meter का focal length होगा उसका. So 1 meter का tube में आप डाल सकते हो.
Okay, thank you.
Okay.
Sir, how can we measure distance between us and star?
Distance between Earth and between us and stars. That's a very long, very nice question. In fact, there are missions which are doing that now. And I did not get time to talk about this, but there's a mission called Gaia, okay, GAIA. You can go search about it. And it has provided measurements to the distance. The concept is very simple. You understand parallax, right? If you're going in a train, you can see that the nearby objects are moving faster compared to the distant ones. So the same technique is used, but by measuring the objects between two different points in the Earth's orbit. Okay, 6 months apart, you observe the same area, and then that's how you measure the distance.
So let us now take one last question for the day.
Yeah.
And so
Hello, sir. Thank you for a wonderful talk.
Yeah.
I wanted to know, like, just how you mentioned the comet 2L Borisov, which was an interstellar comet.
Right.
There was the news of Oumuamua,
Yes.
and I never got to know whether it was an asteroid or comet, and did PRL do some observations on it when it was here?
Okay. So the question is, did we do anything about the first interstellar object? So in fact, the first interstellar object was an asteroid, as she said. And this was an asteroid, which means that it was really faint and it was extremely fast. Okay, so we really did not get much time, and I think the other major reason was that it was visible in the southern hemisphere for more time than in the northern. That is why we could not observe it. Okay, yeah.
So
You want to take one last? Yeah.
सर सब बोलते हैं टूटा तारा, तो वो टूटा तारा होता क्या, उसको टूटा तारा क्यों बोलते हैं?
आई मेंशन मीटियोराइट ना, तो ये मीटियोराइट वही होता है. टूटा तारा मतलब ये दीज आर एक्चुअली दीज माइनर बॉडीज जो मीटियोर्स है, मीटियोरॉइड्स है. When they come and hit the Earth's atmosphere, they burn up in the Earth's atmosphere. So that is another protective thing which the Earth's atmosphere does. That is what protects you from these objects. So that is what they are actually. Yeah. Thanks.
Sir.
So due to the time constraint, we have to move ahead with the event. So Professor Ganesh will be here. You can ask. He'll be happy to answer all of your questions in the next break when we'll be having this. So thank you, Professor Ganesh, for that thought-provoking talk. So it's truly incredible to think of such a giant spaceship. So let us all also take us a moment to appreciate the effort and dedication our speakers have put in to create this event a special one. So with that, we invite our next speaker for the day.
Our fourth speaker is Professor Suresh from IIT Pune. He will introduce an innovative idea, a proposal for a lunar gravitational wave detector. Professor Suresh is a physicist with an interest in testing fundamental physical laws of nature. He has worked in several laboratories across the world, performing tests of gravity and the standard model of particle physics. Since about 2010, he has been part of the LIGO scientific collaboration and has contributed to the installation and commissioning of the LIGO detectors at Livingston and Hanford. Dr. Duravire's primary expertise lies in designing, building, and operating physical experiments. These experiments often involve high-precision measurements at the edge of known technology. He is presently in charge of a training program for a commissioning team which would build and operate the LIGO India gravitational wave detector. Today's talk is titled Shimmy with the Moon. This is about how we can use moon to detect gravitational waves and what that could mean for science. So let's welcome Professor Suresh Dharavali.
Okay.
It's one.
It worked a few minutes ago.
So we'll display the time here.
Time?
So after 30 minutes, we'll display a 5-minute play card. Yeah.
Okay. It's okay. That you can just show me 5. That's all. Don't worry about this. Shall I start? Yeah.
Let's welcome our fourth speaker.
Thank you very much for having me here. Now, Professor Anand Sengupta has challenged me with this title, and so I had to live up to it. So I put up something. I have to shimmy. So today I'm going to talk about a different kind of radiation. You know, so far most of the speakers of today have spoken about how we receive information about stars and galaxies from the universe, and most of it is in the form of light. It comes in the electromagnetic domain, whether it is gamma rays or X-rays or ultraviolet, visible, radio waves, all of that is electromagnetic radiation. Now, gravitational waves are fundamentally a different kind of radiation that comes out of black holes or other massive bodies, especially when they collide and merge. Then they emit a powerful pulse of radiation. Now, this radiation, if you think about light, you know, we sense it with our eyes. This radiation is something related to more like sound, but not sound through air, but sound traveling through the universe. Sound travels through air due to the compressions and expansions of air. Gravitational waves are ripples in the fabric of space-time. That is, the space itself tends to expand and contract when these powerful events such as collisions of black holes, collisions of neutron stars occur. When we have two black holes which are orbiting each other, you must have heard that Einstein has proposed this theory called general relativity, in which he proposed that space around massive bodies is curved. And if something can curve and change shape, it can also generate an elastic, space is like an elastic membrane. And this simulation shows you what happens when there are two black holes which are orbiting each other. What happens to the space? The final moments of a binary black hole, when the black holes approach each other and then they collide or merge, the initial phase is called in-spiral phase here, and there is then the merger, when they meet and fuse into one black body. And then after merger, they vibrate. The resulting black hole vibrates for a small duration of time. That's called the ring down. It vibrates like a bell. During this phase, these are the gravitational waves that are emitted from this event, which the event itself is so powerful that several suns of mass can be converted instantly into radiation. For a moment, it will be the brightest object in the entire galaxy. I didn't do anything. Okay, fine. So this is the merger of two black holes to form a single horizon, and of course, no light is emitted in this process. So you cannot see this if you use a normal telescope. Now, what is the nature of this gravitational wave radiation? It is a lose contact. Why does it keep going off? It's, unless you, maybe it's not loaded because it's in Anand's email. Right.
Did you copy this?
No, it's in Anand's email. Yeah. Yeah, okay. So gravitational waves are primarily transverse in nature, meaning that if there is a direction of propagation, the distortion of space caused by gravitational waves is perpendicular to that. So this is the nature of the propagation of waves. The gravitational waves distort space. If there were a circular object, it would get distorted into an ellipse, and the ellipse would oscillate. So what you see here are oscillations of an ellipse. In one half of the cycle, it will be elongated in the vertical direction. In the next half cycle, it will be fat. It will be elongated in the horizontal direction. So this way of distorting space is characteristic of gravitational waves. Every time I change slide, something happens. Maybe this is causing something. I can change slides with this. Maybe that's easier. I think I'm probably changing the source with this. You switch back. Yeah, remove that. We'll just use this mouse. Yeah, okay. So, to detect these gravitational waves, we have built detectors on Earth. They're called interferometric gravitational wave detectors. There are two in the US. They're called LIGO detectors. They are huge detectors. They're 4 kilometers by 4 kilometers. And we are going to build one like this in India, in the middle of India, near Nagpur and Hyderabad. There are many such detectors around the Earth. There are 5 in total, well, 4 in total which are operational, maybe 5. So there are 2 in the US, 2 in Europe, 1 in Japan, and the 6th one is going to be in India. We need a network of these detectors in order to sense where the objects which are emitting these gravitational wave radiations are present in the sky. The first of these detections came not very long ago. It was in 2015. And this was a collision of 2 black holes. The collision resulted in a there were two objects which were each, one was 35 times the mass of the sun, one was 30 times the mass of the sun, and the resultant was 62 times the mass of the sun. This result was, you can see the difference means that there were three solar masses of material which was instantly converted into radiation. For this particular work, for pioneering these fantastic detectors and opening up a new field, a new way to look at the universe, the pioneers of this field were given a Nobel Prize in 2017. Barry Barish, Kip Thorne, and Rainer Weiss were the three people. But along with them, there were a whole team of about 2,000 scientists who worked in order to make this detection possible. Almost immediately, another extraordinary detection was made, which was the neutron star collision. Now, the difference between a black hole collision and a neutron star collision is that black holes do not emit electromagnetic radiation, so you cannot see them with a normal telescope. Whereas a neutron star collision, you can see it both in normal electromagnetic radiation as well as in a gravitational wave detector. So you can then compare the differences and similarities between these two kinds of radiation and understand them better. For example, one of the predictions of Einstein was that gravitational waves will travel at the speed of light, at the same speed as electromagnetic radiation. This fact could be checked when both these pulses arrived almost simultaneously after having traveled for millions of years. Since the first detection, we have made hundreds of such detections. Some are black hole detections, some are neutron star detections, and we have begun to see things which were not visible to us before. We thought there were only black holes roughly of the size of the sun, maybe a few times more massive than the sun, but then we found out there are 100 times more massive black holes than the sun, which are also possible. The problem with observing something like that is now you have to explain how such a black hole could have formed. What is the evolution track? Can stars coalesce to become black holes of that size? Or do they have to be born right at the beginning of the universe? So these are all open problems which we are trying to understand now, because now there are new information flowing in through a new channel of information, which is through the gravitational wave radiation. I wanted to give you some idea about how this business of detecting these powerful events in the universe happens. First, we do something called source modeling. That is to understand what kind of gravitational waves could be detected in our detectors. We have to understand the source of these gravitational waves. Usually, there are very powerful computers that are used for computing numerical computations to generate a model of the source that generates this. Many kinds of sources are possible, so we have to somehow understand all of them. Then we have the business of detection, where a detector actually senses the received gravitational wave radiation here. Then comes the hard part of understanding what it is that we have detected. What is the nature of that source? What are the parameters of that source? How massive is it? How far away is it? How bright is it? And does it have an electromagnetic counterpart? If it has an electromagnetic counterpart, where is this source so that I can turn my telescope and look at it? So we distribute what are called low latency triggers, which means the moment we detect a gravitational wave event somewhere in the universe, we tell the rest of the world, all the astronomers in the world, hey, we saw an event in this part of the sky. Do you want to turn your telescope and look at that? So then whoever has a telescope free and is capable of watching that particular event, they'll turn the telescope and try to find what we have indicated in the sky. Then we have simultaneous observations, both in gravitational waves and electromagnetism, and we have this entire new field called multi-messenger astronomy, where we try to gather information about these objects across all wavelengths, and including gravitational waves, and try to make sense of what it is that has generated this event in the sky. There are many kinds of gravitational waves from many different kinds of sources, and not all of them have the same wavelength and the same frequency. So we have here, the terrestrial detectors are the LIGO detectors and the advanced LIGO detectors. These detectors are in the relatively high frequency domain. This is in the terms of wavelength, so it's a long wavelength. Sorry, these are short wavelength. And as we go to the left, we have longer and longer wavelengths here. So the mid range is somewhere over here, which is caused by white dwarfs or binary neutron star background and so on. These are not detectable in our terrestrial detectors. For that, we have proposed a space-based mission called LISA. LISA is is an American proposed. Initially, it was a global mission. It's an international project. And it involves a constellation of satellites in a triangular configuration, which follows along in the Earth's orbit. And this is like a $1 billion mission. It takes about 20 years or 30 years to develop this kind of technology that we require. So the proposal was made probably in the mid-80s or late 90s, and people have been working already for 30 years on trying to develop this technology. We will need another 15 years to complete what we require in terms of the ability to launch and make the observations with this constellation. We have already launched a Pathfinder mission for the technology demonstration of this. It's called the LISA Pathfinder. It's a very successful mission. So we are confident that we can do this, and the launch date for this is like 2037. So it will happen in the middle of your professional lives. Now, if you go back and see in between the LISA band and the terrestrial bands, there is a gap, and that's called the decihertz gap. The decihertz gap is a very exciting place because it allows us to see sources which are not visible from LISA and not visible from Earth. It's a mid-gap which is not addressed by any other mission. So several missions have been proposed, a Japanese mission called DECIGO, there are a couple of Chinese missions called Taiji and Tianqin, I think. Then Leela is a very recent mission put up by the USA community. The project that I'm talking about today is called the LGWA. It's called the Lunar Gravitational Wave Antenna. It's a set of seismometers that sits on the surface of the moon. And I don't want to go through the entire explanation of each mission, but we can come back to it if you're curious. This is a set of 4 seismometers which sits on the moon and watches the oscillations of the moon when a gravitational wave passes by. I just wanted to show you the sensitivity of LGWA, which sits in between the LISA band and the terrestrial bands. What is plotted also here is the evolution of for example, a stellar mass black hole, supermassive black hole, or an intermediate mass black hole, or this is a gravitational wave event, the first one, and this is the neutron star event. So the evolution of these events over this frequency scale over time is what is shown here. What this means is that an intermediate mass black hole, a binary, would begin its in-spiral phase somewhere, and it would be visible in the LISA band. After some time, it will move into the LGWA, the decihertz band, and then it will coalesce in the domain of the terrestrial detectors. So before it arrives here, this track will take maybe tens of years to hundreds of years, and we would see it long before it actually happens. So we can anticipate an event before it happens by observing this. Let me talk then, focus on the lunar gravitational wave antenna, the LGWA. This involves essentially, the reason why we are doing it has 2 scientific goals. One is to study the astrophysics of gravitational wave radiation. Also, it helps us because they are seismometers. They sit on the surface of the moon. So we can observe the lunar seismology, and we can image the interior of the moon much better than any other sensor that we have placed on the moon so far. Where are these going to be placed? They are going to be placed in one of the craters. So these are cryogenic sensors, which means that they need to operate in very cold atmosphere. And we have, moon is irradiated, moon receives a lot of sunlight because there is no atmosphere to block. The only places where the sunlight is less is in the polar regions, where we have craters, and the craters provide a rim which is providing a shadow. The sunlight never reaches the bottom of the crater. So the bottom of the craters in the North Pole and the South Pole are so dark that they're called permanent shadow regions. Sunlight never reaches them. It never has in the past 4 billion years or so since the moon formed. So we suspect that there is trapped ice there, which is like a permafrost. It is completely hard and it never goes away. Secondly, the temperatures inside have been measured by satellite flybys, and you can see here the temperature scale. The temperature inside these purple regions is about 41 to 50 Kelvin. That means it is almost 200 degrees colder than the room temperature. And inside those, there are little pale pink patches. Those are actually even half the temperature. They're around 25 to 30 Kelvin in temperature. So those are some of the coldest places you can find naturally in the vicinity of the Earth. So we want to place sensors within those extremely cold spots. There is a reason for that. Because if we do that, then we can invoke the properties of superconductors. You know, superconductors have very nice properties because they have extremely low fluctuations of current flows inside wires. Typically, when you want to make any sensors, you need some kind of electronics, and those electronics generate some kind of noise. The current flowing in wires generates noise, but superconductors don't do that. Secondly, the materials that we use for making these kind of seismometers, the material itself generates some noise, but when you make it very cold, that kind of noise goes down as well. So these are superconducting seismometers. There are cryogenic seismometers which use superconductors. And what I have shown here is one of the seismometers which is placed on the moon. It contains a kind of a leveling platform. On top of that, this pink seismometer. Inside the seismometer, I have blown up this picture on the left. Inside the seismometer, there is a suspended mass, roughly of about 1 kilogram or maybe 5 kilograms or so. It's suspended from two very thin arms, and it's like a pendulum. It oscillates very gently, and you can tune the resonance frequency of this pendulum to be very low. So it makes it a very sensitive inertial sensor. And then we can observe the motion of this suspended mass in multiple ways. You can either use superconductivity itself as a sensor, or you can create an interferometer as a Michelson interferometer and use that. So we are still exploring various ways in which to sense. We can also push that mass around using Meissner effect. Meissner effect is a superconducting effect where a superconductor tries to expel magnetic field from within it, and in that process levitates. It is possible to float a magnet on top of a superconductor. So using similar forces, we can push the inertial mass into place. I can go into the details of this if you're interested, but this is my last slide, I think. Yeah. So I wanted to make a point that there are many nations presently, moon has suddenly become a very exciting place. A lot of people want to go back to the moon. They want to establish permanent stations on the moon as both for research purposes as well as for exploring possibilities of mining and so on. But I'm more interested in the scientific value of moon as a very quiet platform on which we can do things which we cannot do on Earth. So we are at a good time in order to utilize this opportunity to do great science on the moon. And much of these missions require extraordinary technology, which presently does not exist. If you want to go to the polar regions of the moon, as it is, you can see our ISRO is developing the technology to go to the polar regions, to land a craft there. But to land inside a permanent shadow region is an additional challenge. Because in those regions, the temperature is so low that we do not have generally the technology to operate in a permanent shadow region. The second problem in a permanent shadow region is that there is no sunlight. By definition, there is no sunlight, which means you don't have a solar panel. You need to carry your energy. You cannot use a solar panel to get additional energy. But if you have a battery, that battery has to work at 30 Kelvin. Not many batteries do that. So then what do you do? So there's a multitude of technological problems that one has to solve in order to operate a sensor in a permanent shadow region without disturbing your sensor itself. I can say I want to carry a little nuclear reactor and put it there, but it defeats the purpose. We want a very quiet area there. So the technological development necessary for such advanced projects is what most of your generation will be addressing, because these projects take decades to complete. As I said, LISA, for example, is still a technology in development, even though we have a LISA Pathfinder. So in the solving of those technological problems, we generate new science, new engineering, and the knowledge that comes out of these technological missions, these very tough problems at the edge of known technology today, it forces us to invent new technology. And that's where the benefits of that activity accrue back into the society in the form of new technology that all of us can use. So that's the message I wanted to send today. Thank you.
So the floor is now open for questions. I would request the volunteers to please give the mic so I can see some hands up here. Praveen, could you please take the second row?
Good morning, sir.
Morning.
Why the name is given LISA?
The LISA mission?
Yes.
It's the Laser Interferometer Space Antenna.
Okay.
It's just like we had a laser interferometer gravitational wave observatory on Earth. But these things are not like telescopes, but they're more like radio telescopes. They're more like an antenna which receives radiation. So, in fact, the first proposal, which was written by Ray Weiss in, I think, 1981 sometime, he called it a gravitational wave antenna. So that's the reason the name still hangs around.
Okay, thank you.
Yeah. Even this one is called a lunar gravitational wave antenna. So.
Sir, what is the effect of electromagnetic radiation in human beings?
What is the effect of electromagnetic radiation in human beings? Well, by and large, human beings are neutral. We are not positively charged or negatively charged. So if you were to bring a charged plate near me, nothing happens to me. Secondly, there is a lot of electromagnetic radiation which is continuously passing through us. We are not aware of it, in the form of cosmic rays, in the form of gamma rays. They penetrate the Earth's atmosphere and they pass through us quite often. So it's not so uncommon for electromagnetic radiation to pass through a human body, and nothing much happens to us. Unless there is particular radiation, like, for example, microwave radiation, which you use to heat food, in a microwave oven. If you were irradiated with it, the same thing would happen to you as what happens to a potato. You would boil, right? So it's like that. Yeah. Certain radiations can affect you, but most radiation does not.
Sir, as we saw now, gravitational waves are like ripples in the space-time fabric. So multiple events happen at the same time. Here two black holes are colliding, there a neutron star is, something is like happening. And our Earth is also a part of that fabric only. So like how can we correct those inaccuracies? Like if I want to measure the gravitational wave of this object, like that object's gravitational wave is also coming. So like the wave coming will be resultant of both of them. And yes. Some other factors are also there. So how can we compensate all of them?
Yes. So what the question he is asking is, if there are many gravitational wave sources simultaneously occurring and all of the radiation is landing on us, can we distinguish them, or do we just see a total mush, which is a sum of everything that we see? It is true that in certain frequency bands, like for example in the frequency band at which the terrestrial detectors work, it's about 100 hertz to about 1 kilohertz. That's the kind of frequency band. In that band, the events which we have, our detectors so far are not so sensitive that we would very often find two simultaneous events happening at the same time. So at this point we are okay. We get about maybe 10 events per week or 10 events per month, something like that. That's about the rate at which we sense events today. But that is not the case when we go to LISA. LISA is so sensitive to what is called the white dwarf background. This is because there are a large number of such sources, and LISA is sensitive to that. It hears a hum, like, for example, if I listen to the conversation of students in this hall today, I cannot find out which student is saying what. But I know that all of them are speaking, and I can hear all of them simultaneously, so I hear a buzz. And that's what happens in LISA. So we have a gravitational wave stochastic background. It's a random fluctuation. But it is still information, because the stochastic background of radiation that LISA hears is it has a certain frequency shape, it has a certain loudness. So I know that this is not a bunch of lorries honking, and there are students talking. So I can make the difference. I can find out that difference. And the frequency shape, trucks honking have a different frequency than students talking in a hall. So I can tell the difference about the nature of the source that has generated that hum. So it is still, some information can be drawn from that.
Sir, why is the phone's radiation is harmful for our body?
I can't see you. Where are you? Okay, fine, yes. Yeah, please go ahead.
Sir, why phone's radiation is harmful for our body?
Well, I don't think it is, because we have been using phones for like, what now, 15, 20 years, and I have not heard of anybody who was hurt by a phone.
Okay, sir. Thank you.
Good afternoon, sir. As you mentioned about the collisions between neutrons and black holes, so according to relativity, can we have a practical wormhole?
Well, wormholes are a very different object. So far, we have seen theoretical predictions that a wormhole is in principle possible. But I think people have also estimated the energy it requires to create a wormhole. And I think it is much, much larger than what is available in a galaxy or in a universe or something like that. So they are not likely to be seen in nature, even though they are theoretically possible.
So let us take one final question for the day.
Can you give me a warning about where you are? Okay, there, yes.
Sir, how science can use electromagnetic field?
How science
Can use electromagnetic field?
Oh, we do use it every day. I mean, you're using with the microphone there. The electromagnetic field generated that microphone is received by a receiver here. All radio waves are electromagnetic waves. All light is electromagnetic waves we see.
Sir, we all have heard about multiverse and their variants. So what is your opinion on multiverse, and is that real that our variant exists in every multiverse?
So this is an opinion, right? So this is not a hard scientific position of mine. Is multiverses possible? I think theoretically, if our universe can exist, how can we say that another universe like ours cannot exist? Maybe it does, maybe it doesn't. We have not seen one, but is it theoretically possible? Yes, I guess it is.
Thank you, sir.
So beyond that, it's a matter of your personal taste. Do you want to believe that a multiverse exists, or you don't like it and you don't want to believe it? I think it is a matter of taste after that.
So thank you, Professor Davari, for giving us the intriguing insight to what future of lunar exploration might hold for us. So I hope you all are as excited as I am for the future of space exploration. So let us keep this energy up as we call the final speaker for the day. So our final speaker for today is Shri Pranav Singh. This talk is about startup opportunities and careers in space technology for students across all disciplines. Shri Singh is the Deputy Director and Program Management and Authorization of InSpace. InSpace is an autonomous single-window agency to regulate, authorize, enable, promote, and supervise all space activities undertaken in the country. He has 20+ years of experience in the area of high-reliability space-qualified subsystems, design, and systems reliability. He had led the design and development of active systems as Deputy Project Director in CMS-01 program of ISRO. He had led the test and evaluation team to ensure conformance to the specification of satellite subsystems, payloads, and spacecraft through a series of tests to ensure systems reliability. He has collaborated with Indian industries and global foundries for the optimum use of available resources for the Indian space program. This is a must listen for anyone thinking about the future careers and how they might get involved in the space industry. So please welcome Shri Pranav Singh.
Good afternoon. So, thank you, Dr. Anand, Professor Shashi, Dr. Suresh, and Pradeep, and dear participants and volunteers of IIT Gandhinagar. As such, how many are here as a startup? Is anybody is a startup here or final year BTech student? Okay. So I believe most of you are class 5th to 12th. Is it? How many of you in the class 9th? Can you raise your hand? Okay, we have the good audience of the class 9th. Okay, great. So, I will go in my last slide before starting what is the in space and what is my background. Okay, it is not PPT, so. No, we'll go for this. Okay. Still will not go this. Okay. So, for the student, ISRO have the Yuvika program. It is a Yuva Vigyanik Karyakram or Young Scientist program, where if you are in the class 9th and pass out of the class 8, you can apply in the ISRO. I will just go for the career point of view, then we'll come to the background. Where the student or who is the aspiring class 8th student, class 7th, and want to pursue in the technology domain, want to have an experience of ISRO, ISRO have 15-day residential program for the students, where the base level ISRO start interacting with the young generation or the people who want to become scientists or make his career in the space domain. And requirement is you have to apply on our ISRO website under the Yuvika program. It is we do every year and select large bunch of students across the country and facilitate the space domain interacting with the ISRO. And requirement is very simple. Your percentage marks, your interest in the scientific domain, like your score in the different technical programs or national level programs have the weightage. Like if you have participated in the national level scientific quiz, some competition, it have the weightage. If you have if you have participated in the Olympiad and you are the first ranker of state, nation, or the college, it have the some ranking. If you belong not to the city but the small village area, it have also have weightage for the people who belong to the village domain, means not, outside the municipal area. It have weightage to make him at par as the exposure of the city student have. So Yuvika is a program where you get exposure to the ISRO activity, and it is an interest of the class 7th, 8th and 9th student, because 9th student who are appearing admitted in the class 9th and just pass out in the class 9th basically, and not in the 10th are our target audience, or the eligible students participate in the Yuvika program. Then ISRO also do the space on wheels, where we, on the space, what is available, what is the technology ISRO is working, or ISRO not, but the nation is working. We go to the different colleges, cities, and showcase what the scientific technology ISRO is working or the future we are going to working. So you will have a hands-on experience on it. Then space tours and academic courses, all things are for the students who are in the engineering college or the above. We also celebrate, do the different events like World Space Week, Science Days, and Technologies Days, where we interact with the students, call them to the ISRO campuses, showcase what is the interaction with the students of the class 6th, 7th, and engineering college students at the Space Application Center or the Physical Research Laboratory PRL at Ahmedabad. And across the different, because all people are in Ahmedabad, I am talking regarding the Ahmedabad. And we have the Space Exhibition Center at the Ahmedabad, where it is a free, any students except Monday can visit from 10 to 6 o'clock and interact with the retired scientists and working scientists. One or two are there to guide you about the technology, and there is an exposure of the models are available, what are flown in the satellites, actual models as well as the dummy models. So this is the regarding the students, for the students what we have. Now, so I will discuss with the students regarding this figure. You can guess what is this? Means in the launch vehicle, similar shape you might have seen. Anybody can tell which shape is, which look part of the satellite it is? Any guess? It is the top. So it is the satellite you might have seen in the previous video, first video, when Pradeep has shown that there are strap-ons, then first stage separate, second stage separate, and when you go out of the atmosphere, the heat shield separate out. So this is the top location where the this top location is the satellite, where the satellite is mounted. And the rest of the portion below that blue line is that is just a supporting structure to give the thrust to, like you are seeing now, one satellite is coming, we are doing the firing to achieve the velocity. But if it is not a inter means space exploration mission, it is just suppose we want to send a satellite in a LEO, MEO, or the geostationary orbit. This remaining part, after releasing the satellite, is go around the Earth for a month. Or it need as a debris mitigation. One of the question is the first, I think, first presentation it was asked that what happened to these bodies. So these bodies, the remaining body will move around the Earth for months. And this platform now we use for the experiment for the young people, startups, and academia. That is called the POEM platform. Means PSLV experimental module. That is called POEM popularly. Where suppose you are an intermediate student as or a engineering college student, or becoming a engineering college student or science domain, and want to develop small payload or a experiment instead of making satellite, because making satellite is a big thing. You need a solar panel, you need a communication link, and many things to transfer the data to Earth. Now we, using this module which is orbiting the Earth, ISRO has given a platform where you can put your experiment. Suppose a student, suppose here a student of class 9th, 10th, or their college have guiding you to make a real-time experiment of communicating with the satellite, and making you want to make a ground station at the your campus and talk through the satellite to the different school or different campus. You can do this experiment through this POEM platform at the least cost. Means you have to make a receiver and transmitter on the satellite, and we provide as a in-space, make you enable to make such payload and launch to a satellite. We can enable you through our ISRO support to establish a ground station and link, study the total communication behavior through this POEM experiment with the least cost or with the least knowledge of how the satellite can be controlled, monitored, what is the administrative effect, because administration required to maintain a satellite. So these few things are available for the academia and the students to work on the satellite domain. I think how many people know POEM, PSLV Orbital Experimental Platform? Is anybody listened before that? No, so POEM is a platform where you can experiment your idea. Suppose you want to develop a camera, engineering means intermediate or 11th, or nowadays even school colleges of the 9th, 10th students are making cameras, solar panels, and the experiment based on the solar panels or talking between the two stations using the camera, means mobile devices. Similar experiment you can do in the satellite using this platform. And it is a design totally for doing the experiment by the academia, engineering, and startups. And these two things are the academic strengths. The rest I will go now from the first slide. Okay, so first of all, we'll go, what is the in-space? Anybody know here the in-space? You have listened before? ISRO, I think all of you are knowing. In-space, anybody know? So in-space is Indian National Space Promotion and Authorization Center. It is officially inaugurated in June 2022, and its whole purpose is to authorize, enable, promote, and supervise space activity in the India. As space activity is need a very complex technology, we enable you to understand whole technology from with our mentorship as well as our technical team to make and work and use of the satellite technology. Satellite technology is nothing, it is not like that making a satellite only is the satellite technology, or making a launch vehicle is the satellite technology. Utilizing satellite information like the communication, PNT, like GPS, what GPS you are using is nothing but a satellite. So ground application of the satellite technology also come under the satellite domain. So there are many domains. When you want to work on it, in-space is here to support you, enable you, and give you the mentorship through our experts. Okay. So these things are facility, but for the college students, I don't think there is much helpful. And ISRO is, as a government agency, it is spreaded across the nation. In Ahmedabad, we have the two centers of the under DOS. PRL is independent agency, but working in the field of space under the Department of Space. And ISRO have the center, Space Application Center. Then we have the InSpace, which is the new organization to enable and interact with the academia. And if you want to work with the ISRO or you want to need some facility in the ISRO technical facility, we can enable. Like anything you are thinking in the space domain, then we have centers in URSC and different domains. And why I have taken this picture? Because till now you are knowing that the only launches are done by the ISRO in the India. But new change in the new policy enables any private company, like suppose out of you anybody is making their own company. You need not to that you cannot make your launch vehicles. You can make your own launch vehicles as a company in the future, because government has opened the door of space domain from the government to the private. So these are few successful people who have done making the rockets in India, like Skyroot, Agnikul, Ajadisat, and few people are making satellite as well, like Agista BST, Pixel, Dhruva Space. So it is not like that the only ISRO is the only agency at present that making the satellite. Yes, ISRO is making a big satellite, have the big heritage, and we are supporting new organization, new people to come up and make your own satellites. And it's a very simple thing. We will make you to understand that satellite or making rocket is not a rocket science. It's a very simple. And for that, we are conducting a different kind of events like model rocketry, CANSAT event. Like CANSAT is what? Any student, suppose you want to make a satellite, just any 9th, 7th, 5th, you want to make a satellite. You need not to make a satellite and launch it. You can understand this technology on your campuses or on the ground. So yearly, last year we have conducted here in Ahmedabad CANSAT event, where we give a target like a CANSAT. CANSAT means making a satellite in the size of can, means Coca-Cola can, where this concept has come. And we will give you a platform where you can launch this satellite up to a 1 kilometer height and drop it. And you have to design a satellite with help of parachutes so that it descends slowly. And you can install sensor like nowadays sensors are not very costly. Like you can put temperature sensor, humidity sensors, height, GPS receiver, and transmit it. UHF transmitters are very cheap nowadays. And make a system engineering where we will help you in doing this design. PDR means design reviews for its success. And give you a platform. Like launching a CANSAT at 1 kilometer, it is a not easy task. But making a satellite by a student is an easy task. We give you a platform to launch it at the height of 1 kilometer and monitor and have a feel of thus how the satellite will work. Similarly, we are doing the model rocketry. Suppose instead of electronics, you have interest in rocket science and want to send a rocket. Like our nowadays, science centers have the experiments like water rocketry or air-based launching rocket. So similarly, you can launch a fuel-based rocket up to the 1 kilometer height. For that, we are doing the reviews, guidance, as well as we are conducting the events. So these kind of things are helpful to the students. I think there is nobody in the final year students, else we have the PI program that is called Pre-Incubation Entrepreneurship Development Program. I will take 2 minutes to explain it, where we give the financial aid to those who have the idea for developing their own business instead of doing job. So pre-incubation entrepreneurship program is those who are not a startup or incubated anywhere and have just an idea to do something in the space domain. For that, but the minimum qualification is you should be the graduate or going to be graduate, where we will give you 2 lakh rupees plus mentorship to develop your idea in a business. And if your idea is mature and still you are working and time of the 6 months, then our screening committee select your idea, then we further support you to give you 10 lakh rupees and the registering your business as a startup. So these kind of things are available from the Department of Space and different government department to support and inculcate the business orientation mindset within the youth. And this program is for the same. I think rest I will not go because rest are designed for the different audience. Any question you have regarding Yuvika or the poem platform or the pre-incubation entrepreneurship, you can you are welcome. Or any domain regarding to space, you can ask. Anandji, I will not go through the detail because audience is the only students. ठीक है? हाँ, ठीक है. अच्छा.
Sir, please give us some good books names regarding astronomy and space in English as well as Hindi too.
Wow. I will email them or I will ask Shashi Kiranji or Dr. Suresh to tell the book, name of the books. Which book you refer? I will suggest you go to the website called www.isro.gov.in. Second website is www.prl.res.in and isro.gov.in, where you can get many recent things and what is going on in the field of technology. If you are a 10 plus user and having Facebook or LinkedIn account, just subscribe these, follow these their official web pages to have alerts that what is going on in the latest in the domain of technology. Rest for the books, I think you refer to your teacher, it is better. You need not to go out of your curriculum. All the programs never be targeting students to go out of their curriculum. Even the Yuvika program is conducted in a month of, I think start of second week of May to the mid of May, 15 days, so that student curriculum should not be disturbed. So that's why you need not to go different books. You remain in your course and refer to our websites for the updates. Yes, any other question? Thank you. Good afternoon.
What are the career opportunities for a MSc Physics graduate student?
ग्रेट आप तो बताया ही नहीं था MSc फिजिक्स. तो MSc फिजिक्स के लिए बहुत ही अच्छा प्रोफेसर शशि किरण इज हियर, डॉक्टर सुरेश इज ऑल्सो हियर. सो even our previous chairman, Sri S. Kiran Kumar, is also MSc Physics. So we have the very good career for the students of MSc. ISRO treat MSc Physics equivalent to the BTech. It is nothing like that we are treating not MSc Physics. It is another. All optics, most of the optical things, optical domain is led by the physics people only. Like what you are seeing that optical telescopes are made or how the optics will behave, these all at present led by the MSc people only. So we have a good career in MSc Physics in many domains. Like suppose, if you have the idea you apply for my PI program first. I will explain you the PI program. If you have idea and you are the graduate, you can apply for the PI program. Just visit our website, register yourself and put an idea. And if your idea is selected, we will give you during the study 2 lakh rupees. To mature idea to become now I will take a few minutes of you to say that what question we are asking. Because one student is, I have one candidate at least for the Pi program. I will not explain much. I will go was what the. So these are domains. So it is not like MSc Physics do not have a requirement in the space domain. Like suppose any domain you think, like propulsion system, still there is a requirement if it is in the material science or in the launch vehicle or in the satellite communication. And if it is not, application have certain requirement of the MSc students. And they also recruit for the they are the PhD students. Because MSc Physics have a different thinking style compared to the who is doing the engineering. So in application domain, how to interpret the satellite data is the one of the requirement where we take the students of the MSc Physics. Okay. And you can go through our, register yourself in the InSpace website and for the Pi program, which have the last date of 31st August. And we need a certain kind of questions. You apply it and maybe you have the chance to have a mentorship as well as instead of searching job in the ISRO, you may open your own company. Because our whole motto is instead of searching for job, you inspire for the doing your own business, for which we are taking without any guarantee up to means 12 lakh and further as a seed fund up to 1 CR to develop your own business without any stake. So that is the benefit of the Pi program. Okay.
So, thank you so much, sir, for your inspiring ideas and advice.
Great.
The future is bright for all of us. So as we come to the end of this event, I would like to call upon the stage Professor Anand Sen Gupta to deliver the vote of thanks.
So good afternoon, everybody. I'm amazed to see your patience, really. So thank you very much. One thing that stood out for me, after hearing many talks, is that the technological challenges that all our esteemed speakers talked about, they require intergenerational talent to solve. Okay, so you should not think. You should really look forward to what you can contribute in the next 10, 15 years when you become part of ISRO, when you become part of IUCA, or have your own professorship, or if you take up a scientific job, what kind of problems can you solve? Okay, so just to give you an example, many of us, including Suresh here, Professor Suresh, we work on a project known as LIGO. Has anybody heard this name LIGO before? Please raise your hand. LIGO. Gravitational waves. Well, okay. So this is a challenge. This problem was raised in the 1980s, even earlier actually. So it has taken 50 years to kind of come to a point where you can actually deal with this problem and make measurements and benefit from that idea which was seeded 50 years ago. So all these challenges that you heard today, maybe some of you who are in this audience may be able to, kind of deal with these problems and tackle them. So I'll be very happy if that happens. Okay, so we all look forward to that. So it's time to thank a whole bunch of people. It is said that, it takes a whole village to raise a child. Similarly, if you are organizing a conference or a symposium, it takes, just like a village, it takes many, many people to kind of make sure everything is taken care of. And I'd like to first thank IIT Gandhinagar and SAC ISRO, their director's office, for giving us this opportunity to invite you all to the campus. Our deans, Harish PM and Shivapriya Kirubakaran, who almost approved anything that we asked for in order to make this whole program possible. Our LOC members, Suganya, if you are here, please raise your hand. We'd like to, she's there? Yeah. Please give her a very big hand, Suganya. Isha Agarwal. Isha, are you here? Is Isha here? No, okay. Abhishek Sharma. And, there. And our compares today, Akshay And please raise your hand. The people should know. And Divya. Divya, please. That's Divya for you. So, and we have very friendly student volunteers. Nilachal, who is wearing a pie t-shirt. Praveen Patil. Prasad, who has been very, very helpful. And Aparna Rathi. So Aparna has been, again, one of our pillars to get this whole thing done. I'd also like a word for the students and teachers. So we have teachers and students of the following schools here. Nest Public School, DP High School, Green Valley School, Kane Patel International School, Dr. CG English School, and FD High School for Girls. So again, we are very, very grateful that you could send your students. Thank you so much. And I have a special announcement for you, especially a message to all the teachers from these schools, is that it would be very nice, if you could send us 2 or 3 300-word essays written by students who are attending here. If you can shortlist 2 or 3 essays from each of these schools and send them to me along with their photographs, we'd be very happy to actually upload it on our Symposium website. I think that would be very nice. Please take it on. I am sure, please write to us about things that you have heard today, things that you have asked the experts, and if you had a particular moment that you would like to share with us, please do so. Not very long, 300 to 400 words, but please do that. And so I think that will be nice, especially asking teachers to take the initiative. Last but not the least, let me thank the communications and media team. So Vanajakshi, Abhilasha, and Vasudha here is covering that event. We have Mayur Bhatia and Deeptanko, who are, that's Deeptanko. Mayur is also there. So thank you very much. Tej Gurung, Tej is not here, but he helped us make the website at a very, very short notice. You won't believe. So everything worked out. And there are many behind-the-scenes people I have to take their names. So Transportation and Hospitality team at IIT Gandhinagar, Sailesh Patni, Bikubai Patel, and Yashwant Chauhan. So all the delicious food that was arranged at a very short notice, again, was arranged by all these people. So with that, I thank each and every one of you, including all our speakers, for coming here at such a short notice. We are, and making this program a success. I learned a lot and it was very exciting, but it was a bit long. But anyway, I think now it's time for Akshay to make a few announcements before we wrap up. Thank you very much.
So as we are at the end of today's event, I would like to thank you for all your participation and enthusiasm. It's been a day full of learning, and I hope you guys enjoyed it as much as we enjoyed hosting it. So we'll break for now. We have snacks and refreshment just outside the campus, just outside the auditorium. You can exit the right gate. Sorry for the typo. So I would request the accompanying teachers so we have snacks arranged just outside the auditorium, and we have also the buses arranged just where they dropped in the academic block 1 parking, just as they dropped you in the morning. So thank you everyone, and let's break for the day.